Welcome back, everyone. What you are about to hear over the next 2 hours will challenge everything you think you know about the most remote, the most mysterious, and the most extraordinary place on the face of this earth. We are talking about Antarctica, a continent so vast, so cold, so deeply strange, that even the scientists who dedicate their entire lives to studying it will tell you, with complete honesty, that we have barely scratched the surface of what lies beneath. Please let us know in the comments where you are watching this history video and what time you are watching it. And be sure to subscribe to the channel for future videos. Antarctica. Just saying the word conjures images of endless white, of blizzards so fierce they can tear the skin from your face, of temperatures so low that exposed metal will burn you like fire, of a silence so profound and so complete that explorers have reported hearing their own heartbeats echoing back at them across the ice. It is a place where the wind howls at over 200 miles per hour, where the sun disappears for 6 consecutive months, and where the darkness that follows is not the soft, comfortable darkness of a bedroom at night, but rather a crushing, absolute blackness that presses down on everything like a physical weight. And yet, and this is what makes Antarctica so endlessly, almost maddeningly fascinating, it is also a place of breathtaking, impossible beauty. A place where the ice glows blue and green from within, where waterfalls run red as blood, where mountains older than almost anything else on the planet thrust upward through frozen sheets that are miles thick. A place where life, stubborn, remarkable, utterly improbable life, finds a way to exist in conditions that should, by every reasonable measure, be completely and totally hostile to its survival. This is the story of Antarctica. Not just the myths, not just the legends, not just the conspiracy theories that swirl around this continent like the storms that never seem to stop circling its shores, though we will get to all of those, and we will examine them seriously and honestly, because some of them are genuinely interesting even when they turn out to have perfectly rational explanations. No, this is also the story of the real Antarctica, the Antarctica of cutting-edge science and extraordinary discovery. The Antarctica of autonomous submarines plunging beneath glaciers that could reshape coastlines around the entire world if they collapse. The Antarctica of ancient zircon crystals that carry within them geological memories stretching back billions of years. The Antarctica of creatures living in the deep dark beneath ice shelves, in conditions so extreme that their very existence forces us to rethink our entire understanding of where life can and cannot exist. We are going to take this journey together, and I promise you, by the time we are done, you will never think about this continent the same way again. So let us begin at the beginning, or rather, let us begin where most people begin when they start thinking seriously about Antarctica, which is with the question that seems almost too obvious to ask, but is actually far more interesting than it first appears. Why does Antarctica feel so different from everywhere else? There are 7 continents on this planet. 6 of them, despite their many differences, share certain fundamental qualities. They have been explored, they have been mapped, they have been settled, farmed, fought over, built upon, carved up, and claimed. Their mountains have been climbed, their rivers have been traced to their sources, their forests have been walked through and catalogued. Even the most remote corners of these continents, the deepest jungles of the Congo, the highest reaches of the Himalayas, the most isolated stretches of the Siberian tundra, have been visited by human beings, documented, named, and in some sense understood. Antarctica is different. Antarctica covers approximately 5.5 million square miles, making it the 5th largest continent on Earth. It is larger than the entirety of Europe. It contains approximately 70% of all the fresh water on the planet, locked up in ice sheets that in some places reach a thickness of nearly 3 miles. Its highest point, the Vinson Massif, stands at 16,050 feet above sea level. Its lowest point in the Bentley Subglacial Trench plunges to over 8,000 feet below sea level, a depression so deep that if all the ice above it were removed, it would be one of the deepest points on the surface of the Earth. And yet, despite all of this, despite its enormous size, despite its extraordinary features, despite the fact that it has been known to the outside world for over 2 centuries, Antarctica remains, in a very real and meaningful sense, unexplored, unmapped in its deepest details, fundamentally, stubbornly mysterious. Think about what that means for a moment. In the 21st century, when satellites can photograph individual license plates from orbit, when the internet has put virtually all of human knowledge at anyone's fingertips, when we have landed spacecraft on comets and sent probes to the edges of the solar system. In this age of almost unimaginable technological capability, there is still a continent on our own planet that we do not fully understand. A continent beneath whose ice sheets lie mountain ranges we have never seen, lakes we have never visited, ecosystems we have never studied, and geological formations that have never been touched by human hands. That is extraordinary, and it is, I would argue, a large part of why Antarctica has become such fertile ground for mystery, for legend, and yes, for conspiracy theories. When you have a place that is simultaneously real and accessible and yet fundamentally unknown, the human imagination tends to rush in to fill the gaps. We cannot help it. It is what we do. So let us talk about some of those stories. Let us talk about what people believe and what they claim to know about Antarctica's hidden secrets. And then, after we have done that, let us talk about what we actually know. Because the truth, as it turns out, is in many ways more remarkable than any of the stories. The conspiracy theories surrounding Antarctica are numerous, varied, and some of them are genuinely creative. We are not going to mock them or dismiss them without examination, because I think that approach is both intellectually lazy and ultimately unsatisfying. Instead, we are going to look at them seriously, consider what evidence exists for them, and try to understand why these particular stories have captured so many people's imaginations. The first and perhaps most pervasive category of Antarctic conspiracy theory involves the idea of restricted zones, areas of the continent that are, according to these theories, deliberately hidden from public view and protected by military force. The claim goes something like this. Certain portions of Antarctica have been designated as off-limits not for the scientific or environmental reasons that are officially given, but because those areas contain something that the powers that be do not want ordinary people to see or know about. Exactly what that something is tends to vary depending on who is telling the story, but common candidates include ancient ruins of lost civilizations, crashed spacecraft or extraterrestrial artifacts, entrances to underground facilities, or evidence of geological features that would upend our current understanding of the planet's history. Now, it is true that Antarctica has restricted areas. The Antarctic Treaty, which was signed in 1959 and has since been ratified by 54 countries, designates certain zones as protected for scientific or environmental reasons. There are areas around active research stations that are restricted for safety reasons. There are zones around particularly sensitive ecosystems that are protected to prevent contamination. There are portions of the continent where military activities of certain kinds are prohibited. All of this is real, all of it is documented, and all of it is, on its face, entirely reasonable. But conspiracy theorists point to something more specific. They talk about zones that appear on satellite imagery as oddly blurred or pixelated, as though someone has deliberately obscured what is there. They talk about flight paths that seem to go around certain areas rather than over them. They talk about researchers who have allegedly returned from Antarctic expeditions with strange stories and a marked reluctance to discuss certain things they claim to have seen. Are any of these claims credible? The honest answer is, some of them are more interesting than others, and almost none of them hold up to close scrutiny. The blurred satellite imagery, for instance, almost invariably turns out to have perfectly mundane explanations. The particular satellite or mapping software being used, weather conditions at the time the image was taken, the limitations of the technology involved. The flight path anomalies are similarly explicable. Antarctica is a difficult flying environment, and flight paths are determined by a complex combination of weather, geography, fuel efficiency, and the location of airstrips, not by the desire to avoid mysterious hidden zones. But here is what is genuinely interesting about these theories, even when the specific claims don't hold up. They point to something real, which is that Antarctica genuinely is a place where significant things happen outside of public view. Not because of conspiracy, but simply because of logistics. The continent is so remote, so expensive to reach, so difficult to operate in, that the vast majority of research conducted there is simply not covered by mainstream media. Scientists go do extraordinary work, come back with remarkable findings, and the public never hears about it, not because anyone is hiding it, but because the mechanisms of media attention just don't work that way. So there genuinely is a gap between what is happening in Antarctica and what the general public knows about it. Conspiracy theories rush in to fill that gap, often with far more dramatic content than the actual science, but the gap itself is real. Another category of Antarctic conspiracy theory focuses on what we might loosely call military secrets. The claim here is that various nations, usually the most powerful ones, have established secret military facilities on or beneath the Antarctic ice, in violation of the Antarctic Treaty's prohibition on military activities. These facilities are alleged to serve various purposes: advanced weapons testing, surveillance operations, research into exotic technologies, or in more extreme versions of the theory, the operation of underground bases of considerable size and sophistication. Again, there is a kernel of truth embedded in these theories that makes them worth examining. The Antarctic Treaty does prohibit certain military activities, but it explicitly permits military personnel and equipment to be used for scientific research. And in practice, the line between those two categories can sometimes be blurry. Many of the research stations on the continent are staffed at least in part by military personnel. Some of the logistics operations, the aircraft, the ships, the equipment, are military-grade or actually military-operated. The communications infrastructure used in Antarctica has obvious dual-use potential. Does this mean there are secret weapons facilities buried beneath the Ross Ice Shelf? Almost certainly not. The logistics alone would be staggering, the cost of secretly constructing and maintaining anything of significant size in Antarctica, while also keeping it hidden from the satellite surveillance capabilities that multiple nations now possess, would be essentially prohibitive. But does it mean that military interests and activities are completely absent from Antarctica? No, it does not mean that either. The honest picture is somewhere in the middle. Military involvement in Antarctica is real but routine, and nowhere near as dramatic as the conspiracy theories suggest. Then there are the stories about creatures. This is where we move away from political conspiracy and into something more primal, the deep human fascination with unknown animals, with things that might be living in the darkness of unexplored places that we have not yet discovered and catalogued. Some of these stories are straightforward and easy to address. The striders, tall, thin, multi-limbed creatures alleged to have been photographed or filmed moving across the Antarctic ice, are the product of a combination of optical illusions, photographic artifacts, and in some cases, deliberate hoaxes. The human visual system is extraordinarily good at finding patterns, and particularly good at finding things that look like living creatures in random visual noise. It is the same phenomenon that makes us see faces in clouds or figures in the grain of wooden panels. Show someone a blurry, low-resolution image of a snowy Antarctic landscape and ask them to look for something unusual, and they will find it not because it is there, but because that is how perception works. The Nan creature, a name that appears in certain fringe internet communities, is somewhat harder to address simply because the descriptions of it vary so wildly that it is not entirely clear what exactly the proponents of this theory believe they are talking about. In general terms, it seems to involve claims of large, unidentified creatures spotted in Antarctic waters, sometimes described as resembling a kind of giant, unknown marine mammal. The Antarctic Ocean is genuinely home to extraordinary marine life, including species that were unknown to science until relatively recently. So the idea that there might be large marine animals in these waters that we have not yet catalogued is not inherently absurd, but the specific claims about the Nan creature tend to rely on evidence that is, to put it charitably, extremely thin. Here's something genuinely interesting, though. The waters around Antarctica really do contain remarkable creatures, some of them quite large, some of them only recently discovered. The colossal squid Messinichoteuthis hamiltoni was known for most of the 20th century only from fragments found in the stomachs of sperm whales. Complete specimens were not confirmed until 1925, and the first live adult specimen was not caught until 2007. This is a creature that can reach lengths of 14 feet and weights of over 1,000 pounds, and it was essentially unknown to science for the vast majority of recorded history. The lesson here is not that sea monsters are real, but that the Antarctic Ocean genuinely does hide remarkable things, and the history of biology in this region really is a history of one extraordinary discovery after another. Let us talk for a moment about the geography of Antarctica itself, because to understand the mysteries of this continent, both the real ones and the imagined ones, you need to have some sense of what kind of place it actually is. Antarctica is divided into two main regions by the Transantarctic Mountains, one of the longest mountain ranges on Earth. To the west lies West Antarctica, which includes the Antarctic Peninsula, the long, thin finger of land that reaches toward the tip of South America, as well as the West Antarctic ice sheet and the crucial Thwaites Glacier, which we will spend considerable time discussing later. To the east lies East Antarctica, which is larger, higher in elevation, and in general colder and more stable. East Antarctica contains the South Pole itself, as well as some of the most extreme environments on the planet. The Transantarctic Mountains are extraordinary in their own right. They stretch for approximately 2,200 miles across the continent, making them one of the longest mountain chains on Earth. And they are ancient. Some portions of these mountains contain rocks that are over 500 million years old, formed during periods of geological activity that long predate anything remotely resembling the Antarctica we know today. We will come back to those ancient rocks and what they tell us about the continent's history, because that story is one of the most fascinating in all of geology. Beneath the ice, and this is something that even people who know Antarctica reasonably well often find surprising, is not simply flat ground. The bedrock of Antarctica is extraordinarily varied. There are mountain ranges buried under miles of ice that are taller than anything in the Alps. There are valleys deeper than the Grand Canyon hidden beneath the ice sheet. There are plains and plateaus and basins of enormous extent. And there are lakes, hundreds of them, spread across the continent that have been completely isolated from the surface world, sealed under kilometers of ice for millions of years. These subglacial lakes are among the most intriguing features of the continent, and we will discuss them in considerable detail. The largest of these subglacial lakes is Lake Vostok, which lies beneath approximately 2.5 miles of ice near the Russian Vostok Research Station in East Antarctica. Lake Vostok is enormous, comparable in size to Lake Ontario, one of the Great Lakes. It is approximately 160 miles long and 30 miles wide, with depths reaching over 2,600 feet. And it has been isolated from the surface by the best current estimates for somewhere between 15 and 25 million years. That is an almost incomprehensible span of time. For context, 25 million years ago, our human ancestors had not yet diverged from the ancestors of modern chimpanzees. The world looked fundamentally different. And through all of that time, Lake Vostok has sat in darkness, sealed beneath its ice, doing whatever it has been doing in the absence of sunlight, in the absence of surface world inputs, in conditions that should, and yet apparently do not, preclude life. Because in 2012, when Russian scientists drilled through that 2.5 miles of ice and extracted water samples from Lake Vostok, they found something extraordinary. They found evidence of microbial life. Not just a few organisms, but a genuinely diverse community of microbes, including species that had never been seen before. The exact nature and extent of life in Lake Vostok is still being studied and debated, but the basic finding that life exists there in a lake that has been cut off from the rest of the world for millions of years, in total darkness, under enormous pressure, in water that is technically below the normal freezing point but kept liquid by that pressure, is now well established. What does that mean? It means that life is more adaptable, more resilient, more extraordinarily persistent than we had imagined. It means that the conditions we once thought were prerequisite for life, sunlight, moderate temperatures, connection to the broader biosphere, are not actually prerequisites at all, but merely preferences. And it means that when we look at other worlds, at the ice-covered moons of the outer planets, at places like Europa and Enceladus that may harbor liquid water beneath their frozen surfaces, the existence of life there becomes significantly more plausible. Now, before we go any deeper into the scientific discoveries, let us spend some time with a few more of the myths and legends that surround this continent, because they reveal something important about how humans relate to unknown places, and because some of them are entertaining enough to deserve serious attention even when they are ultimately unfounded. One of the most persistent legends associated with Antarctica involves the idea of a hidden warm region, a place within or beneath the continent where temperatures are significantly higher than on the surface, potentially warm enough to support complex life. This idea has appeared in various forms over the decades, from 19th century exploration narratives that speculated about open polar seas, to 20th century theories about geothermal activity creating warm zones beneath the ice, to more recent internet-era claims about underground civilizations existing in thermally heated subterranean spaces. The truth is that geothermal activity does exist in Antarctica. There are active volcanoes on the continent, most notably Mount Erebus, one of only a handful of volcanoes in the world with a persistent lava lake. Mount Erebus has been continuously erupting for decades, its summit caldera filled with molten rock, its slopes dotted with extraordinary ice fumaroles, towers of ice formed when hot volcanic gases meet the extreme cold of the Antarctic air, creating chimney-like structures of remarkable beauty. The heat generated by Erebus's volcanic activity does create localized areas of warmth that support unusual plant and animal communities. And geothermal heat beneath the ice sheet contributes to the melting of the ice at the base of the sheet, contributing to the formation of subglacial lakes like Vostok. But the leap from geothermal activity exists in Antarctica to there is a hidden warm region supporting a secret civilization is an enormous one, and the evidence for the latter simply does not exist. The geological surveys of Antarctica, while incomplete, are detailed enough that a large thermally active region warm enough to support complex life would almost certainly have been detected by now. The heat signatures that would accompany such a region would be visible to the satellite-based sensors that have been monitoring Antarctica for decades. That said, and this is worth saying clearly, there genuinely are places beneath the Antarctic ice where temperatures are significantly higher than the surface average. In deep subglacial valleys, the combination of geothermal heat and the insulating properties of the overlying ice can create conditions that are far from the murderous cold of the surface. Some subglacial lakes have temperatures well above freezing. The bedrock itself in geothermally active areas can be quite warm. These are real phenomena, scientifically documented, genuinely remarkable. They just do not, unfortunately for the legend, involve any civilizations. Another story that has circulated widely in certain corners of the internet involves what is described as a mysterious doorway visible in satellite images of the Antarctic coastline. This alleged doorway, a rectangular opening in a cliff face, perfectly geometrical in a way that suggests human or non-human construction, has been the subject of considerable speculation. Is it the entrance to an underground base, a remnant of an ancient civilization, evidence of extraterrestrial activity? The answer, when examined carefully, is considerably more prosaic. Rectangular and geometrically regular openings in rock formations are not actually unusual in geology. The processes of erosion, freeze-thaw cycling, and rock fracturing along natural joints and bedding planes can produce openings that look startlingly regular. Antarctica's extreme temperature variations, the surface can swing by many tens of degrees between summer and winter, accelerate these processes considerably. The specific doorway that most commonly appears in these internet discussions, when examined by geologists, turns out to be a perfectly natural rock formation, striking in its regularity but unremarkable in terms of origin. This is worth dwelling on for a moment because it illustrates a broader point about the relationship between human perception and the natural world. We are pattern-seeking creatures. Our brains evolved in an environment where the ability to recognize patterns, to distinguish predator from background, to identify edible plants, to read social signals from other faces, was literally a matter of life and death. That pattern recognition capability is extraordinarily powerful and useful, but it also leads us sometimes to find patterns where there are none. To see rectangles as doorways, to see faces in ice formations, to see evidence of intelligent design in the products of geological processes that have no intelligence behind them at all. The story of the alleged 400-foot ice ship is similarly instructive. At some point, a satellite image circulating online was interpreted by some as showing the outline of a massive vessel, a ship of extraordinary size, apparently encased in or resting upon Antarctic ice. The image is striking and the interpretation is understandable, but here, too, the geological explanation is more interesting than the legend. What the image actually shows is a tabular iceberg, or possibly a portion of an ice shelf, in which natural processes have created what appears to be a vessel-like shape. Tabular icebergs, flat-topped, steep-sided masses of ice that break off from ice shelves, can be enormous, sometimes stretching for miles. They can also develop unusual shapes as they melt and erode at the edges, shapes that our pattern-hungry brains are quick to interpret as familiar objects. A long, narrow tabular berg with a high, straight cliff on one side can look, in the right light and from the right angle, remarkably like the hull of a ship. Add some shadows and low image resolution, and you have your 400-foot ice ship, and then there are the pyramids. Perhaps no Antarctic feature has generated more internet excitement over the past decade than the so-called Antarctic pyramids, mountain peaks visible in aerial and satellite photographs that have a distinctly pyramidal shape, their four sides rising at roughly equal angles to meet at a sharp point at the summit. The claims made about these formations range from the relatively modest. They suggest the continent had a different climate in the past, when such formations could have been constructed, to the extravagant. They are actual pyramids, built by a lost civilization or by extraterrestrial beings, thousands of years before the continent was covered in ice. Here is the truth about the Antarctic pyramids, and it is genuinely interesting even without the conspiracy theory overlay. They are real, they are striking, they are scientifically significant, and they have a perfectly natural explanation that tells us something important about the geology of the continent. The formations in question are a type of feature known as a nunatak, a mountain peak or ridge that projects above the surface of a glacier or ice sheet. Nunataks are common in glaciated regions around the world, and they often have unusual shapes precisely because of the way glacial erosion works. When glaciers on multiple sides of a peak erode it simultaneously, they can sculpt it into a shape with flat faces and sharp ridges, a shape that, in extreme cases, becomes almost perfectly pyramidal. This process produces what geologists call a horn, and the most famous example is the Matterhorn in the Alps, which has the same basic shape as the Antarctic pyramids and the same basic origin. The pyramidal shape is not evidence of construction, it is evidence of glacial erosion, one of the most powerful and widespread sculptural forces on the planet. But here is what is genuinely interesting about the Antarctic pyramids. Their very existence tells us something significant about the continent's past. For a nunatak to develop the kind of exposed, sharply defined faces that make these formations look like pyramids significant portions of those rock faces must have been exposed to weathering processes, wind, rain, freeze-thaw cycling, for considerable periods of time. This means that the rock was not always buried under ice. At some point in the geological past, these mountains stood fully exposed above the ice line, or perhaps above no ice at all, in a climate very different from today's. The evidence of ancient exposure is there in the rock itself, in the weathering patterns and the presence of certain minerals that form only under surface conditions. So the Antarctic pyramids are not the work of lost civilizations. But they are, in their own way, genuine evidence of a lost world, of an Antarctica that was once warmer, less glaciated, perhaps even in the very distant past forested. We will come back to that ancient history in detail, because it is one of the most remarkable stories in all of Earth science. Now let us turn to something that is, in my view, more fascinating than any conspiracy theory, the actual history of human exploration in Antarctica. Because that story is one of extraordinary courage, extraordinary suffering, and extraordinary discovery, and it deserves to be told with the seriousness it warrants. The existence of a southern continent had been theorized for centuries before it was actually confirmed. Ancient Greek philosophers speculated that there must be land at the southern extreme of the world to balance the landmasses of the north, a concept they called Antarctos, the opposite of Arctos, the bear, which was what they called the northern sky. Medieval and Renaissance maps sometimes showed a large southern continent, variously labeled Terra Australis Incognita, the unknown southern land, extending far into the southern hemisphere. But these were theoretical constructs, not based on any actual observation or exploration. The first confirmed sighting of the Antarctic mainland is generally attributed to the year 1820, when multiple expeditions operating in the Southern Ocean, from different nations, with different purposes, apparently entirely independent of one another, reported seeing land that could only be the Antarctic continent. Within a few years, sealers and whalers were operating in Antarctic waters, though the conditions were so brutal and the rewards so uncertain that the continent itself remained largely unexplored for decades. The great age of Antarctic exploration began in earnest at the end of the 19th century and continued through the first decades of the 20th. These expeditions, Belgian, British, Norwegian, Swedish, French, Japanese, collectively began to map the coastline and interior of the continent, establishing the basic geographical facts that are now taken for granted. But the cost was staggering. Antarctica, it turned out, had no intention of yielding its secrets without a fight. The expeditions that attempted to penetrate its interior encountered conditions that pushed human endurance to its absolute limits and beyond, and the history of Antarctic exploration is studded with tragedies and near tragedies that remain among the most harrowing stories of survival ever recorded. The most famous of these stories is the race to the South Pole, which culminated in 1911 and 1912 in what is still regarded as one of the greatest human dramas in the history of exploration. Two expeditions, one Norwegian and one British, set out in the same season with the same goal, to be the first to reach the geographic South Pole. The Norwegian expedition, led by Roald Amundsen, reached the pole on December 14, 1911, planted their flag and returned safely to their base camp. The British expedition, led by Robert Falcon Scott, reached the pole on January 17, 1912, 34 days later, only to find the Norwegian flag already there. And then on the return journey, all 5 members of Scott's polar party died, not dramatically, not all at once, but slowly in a tent, trapped by a blizzard 8 miles from a food depot that could have saved their lives. The contrast between the two expeditions, the Norwegian success and the British tragedy, has been analyzed and debated for over a century, and the lessons drawn from it are many and varied. But one thing that is universally acknowledged is this: both expeditions were acts of extraordinary human courage, conducted in conditions of almost unimaginable difficulty, in service of the very human desire to go further, to see what is there, to push back the boundaries of the unknown. And that same spirit, that same fundamental drive to know, is what animates the scientists who study Antarctica today, even if the specific hardships they face are somewhat less extreme than those faced by Scott and Amundsen. The modern era of Antarctic science began in earnest with the International Geophysical Year of 1957-1958, a coordinated international scientific effort that established a network of research stations on the continent and laid the foundations for the Antarctic Treaty that followed 2 years later. The treaty, which came into force in 1961, has remained one of the most successful examples of international scientific cooperation in history. It designates Antarctica as a continent devoted to peace and science, prohibits military activities beyond logistical support, prohibits nuclear testing and the disposal of nuclear waste, and establishes a framework for sharing scientific findings among nations. Today, there are approximately 70 permanent and seasonal research stations on Antarctica, operated by 30 different countries. These stations house anywhere from a handful of scientists in winter to several thousand during the summer research season. They are spread across the continent, from the relatively accessible Antarctic Peninsula to the remote high plateau of East Antarctica, and they conduct research across an astonishing range of disciplines: glaciology, oceanography, atmospheric science, biology, geology, astronomy, and more. Because, and this is something that is not widely appreciated, Antarctica is not just a laboratory for studying the continent itself. It is a laboratory for studying the planet. The ice sheets contain within them a record of Earth's atmospheric history stretching back hundreds of thousands of years, preserved in the form of tiny air bubbles trapped when the snow fell and was compressed into ice. By drilling into these ice cores and analyzing those ancient air bubbles, scientists can measure the concentrations of greenhouse gases in the atmosphere at different points in history, track how temperatures have varied over geological timescales, and understand the natural cycles that have driven climate change in the past, knowledge that is invaluable for understanding what is happening today and what might happen in the future. The atmospheric clarity of Antarctica also makes it an extraordinary site for astronomical observations. With no light pollution, minimal atmospheric water vapor, which interferes with certain kinds of observations, and the specific conditions of the polar environment, the South Pole is one of the best places on Earth to observe the universe. Telescopes at the South Pole Station have made important contributions to our understanding of the cosmic microwave background radiation, the faint afterglow of the Big Bang, and of phenomena at the very edge of the observable universe. But let us now turn to one of the most astonishing recent discoveries in Antarctic science, a discovery that strikes at the heart of one of the oldest questions in biology. Where can life exist, and how far can the conditions of life be pushed before life itself gives up? The answer, as Antarctic researchers have been discovering with increasing clarity over the past few decades, is that life can exist in places that we would previously have confidently described as lifeless. And the most dramatic examples of this are found not on the surface of the ice, not in the relatively hospitable waters of the open ocean, but deep beneath the ice shelves in a world of total darkness, extreme cold, crushing pressure, and almost complete isolation from the sun-powered food webs that underpin virtually all other life on Earth. Ice shelves are the portions of the Antarctic ice sheet that have spread out over the ocean, vast, flat-topped platforms of ice floating on the sea, anchored to the land behind them, reaching in some cases hundreds of miles out from the coastline. The Ross Ice Shelf, the largest of these, covers approximately 188,000 square miles, roughly the size of France. It is, in places, over 2,000 feet thick. And beneath it, between the bottom surface of the ice and the seafloor below, there is a water column of variable depth, in some places just a few meters, in others considerably deeper, that is completely sealed from the outside world. Until relatively recently, the conventional scientific assumption was that these cavities beneath the ice shelves were essentially barren. How could they not be? There is no sunlight. The water is extremely cold. Near or below the normal freezing point of seawater, ice shelf cavities can have water temperatures slightly below 0 degrees Celsius because the pressure of the overlying ice lowers the freezing point. Food inputs from above are effectively zero. There is no mechanism by which organic material from the surface ocean can reach these cavities in significant quantities. By every metric we typically use to assess the habitability of a marine environment, the cavities beneath Antarctic ice shelves should be essentially uninhabitable. They are not. In 2021, a team of scientists drilling through the Filchner ice shelf, one of the major ice shelves on the eastern side of the Weddell Sea, made a discovery that genuinely shocked the scientific community. They drilled through 2,860 feet of ice, intending to study the water and sediment beneath. What they found when they lowered a camera into the resulting borehole was not the expected barren mudflat. Instead, they found a boulder on the seafloor, approximately 160 miles from the nearest open water, and on that boulder they found animals. Stationary animals, sponges, and other organisms that resembled those found in conventional Antarctic seafloor communities, just sitting there, in the dark, under the ice, 160 miles from the open ocean. This was extraordinary for multiple reasons. Stationary animals like sponges are filter feeders. They survive by straining organic particles out of the water flowing past them. To sustain a community of filter feeders, you need a supply of organic material. But in a cavity beneath an ice shelf, 160 miles from any open water, where is that organic material coming from? What are these animals eating? How are they surviving? These questions remain genuinely open, actively debated in the scientific literature, and the answers, when they come, will almost certainly be deeply interesting. One hypothesis involves the idea that currents within the sub-ice cavity system can transport organic material from areas closer to the ice shelf edge, where photosynthesis-based production is possible, into the deep interior. Another hypothesis involves chemosynthesis, the production of organic material not through photosynthesis but through chemical reactions, typically involving hydrogen sulfide or other chemical energy sources. Chemosynthetic ecosystems are known to exist at hydrothermal vents and cold seeps on the deep ocean floor, and it is possible that similar processes are supporting life in sub-ice shelf environments. But the 2021 Filchner discovery, dramatic as it was not isolated. It built on a growing body of evidence, accumulated over the preceding decade and more, that the waters beneath Antarctic ice shelves are far richer biologically than anyone had expected. And some of the most compelling of this evidence came from an entirely different kind of investigation, one that was not drilling down through ice, but swimming. The use of remotely operated vehicles, or ROVs, and autonomous underwater vehicles, or AUVs, has transformed our ability to explore the undersides of Antarctic ice shelves. These robotic submarines, operated either by remote control or pre-programmed to follow specific routes, can dive beneath the ice and cruise through the sub-ice cavity, transmitting video and collecting scientific data in real time or storing it for later download. And what they have found in these dark, cold, isolated waters has been consistently, repeatedly surprising. Corals growing beneath the ice. Enormous, intricate colonies of coral in the cold and the dark, in waters that reach temperatures well below what we typically associate with coral reefs. These are not the warm water, shallow sea corals of tropical reef ecosystems. They are cold water corals, a different group of organisms that are adapted to very different conditions. But they are corals nonetheless, and their existence beneath the ice challenges our instinctive assumption that coral means warmth and sunlight. Sponges, thousands of them covering the rocky seafloor beneath the ice in dense aggregations, some of them of considerable age. Antarctic sponges can live for extraordinary periods of time. Some estimates suggest that certain species can reach ages of more than 1,000 years, growing extremely slowly in the cold water. A large sponge sitting on the seafloor beneath an ice shelf may have been there, growing since long before the first humans reached the continent. Sea spiders. These are extraordinary creatures, not true spiders despite the name, but a group called pycnogonids that are found throughout the world's oceans but reach their most extreme development in the Antarctic. Antarctic sea spiders can grow to considerable size, with leg spans reaching up to 25 centimeters, about 10 inches. They prowl the seafloor beneath the ice on their long, impossibly thin legs, feeding on sponges and other sessile organisms. They are, in a word, alien-looking. They are also real, plentiful, and genuinely fascinating. And octopuses. The discovery that octopuses live in the waters beneath Antarctic ice shelves was perhaps the most surprising single finding in sub-ice biology. Octopuses are, in popular imagination, warm water creatures, associates of tropical seas and coral reefs. But Antarctic octopuses have been doing quite well for themselves in these extreme conditions, and they have made some extraordinary adaptations that have caught the attention of researchers interested not just in ecology, but in biochemistry. The blood of Antarctic octopuses contains a modified form of hemocyanin, the copper-based oxygen-carrying protein that serves the same role in octopus blood that hemoglobin serves in ours, that is particularly efficient at binding and releasing oxygen at low temperatures. In warmer water, this adaptation would actually be a disadvantage, making the protein less efficient. In cold Antarctic water, it is a crucial advantage, allowing these animals to stay active and well oxygenated in conditions that would incapacitate most of their relatives from warmer seas. This brings us to a broader theme that will run through the rest of our exploration of Antarctica: the relationship between extreme environments and extraordinary biology. Antarctica is, from a biological perspective, one of the most challenging environments on the planet. Temperatures are extreme. Resources are scarce. The ice and darkness of winter impose severe limitations on photosynthesis-based food production. And yet life has not merely clung on in this environment, it has, in many respects, thrived. The adaptations that Antarctic organisms have developed to survive in these conditions are among the most remarkable in all of biology, and studying them has paid scientific dividends that extend far beyond the continent itself. Consider the antifreeze proteins found in Antarctic fish. These proteins, technically known as antifreeze glycoproteins or AFGPs, were first discovered in Antarctic not-athenoid fish in the 1970s. The discovery came with a puzzle. The water in which these fish live is, in some areas, actually at or slightly below the normal freezing point of seawater. By all rights, the fish should freeze solid. The antifreeze proteins solve this problem by binding to ice crystals as they form in the fish's body fluids and preventing them from growing larger, essentially stopping the crystallization process in its tracks, keeping the fish's body fluids liquid even at temperatures below their normal freezing point. This discovery was scientifically important in itself, but its implications went further. Antifreeze proteins have since been found in a wide variety of cold-tolerant organisms, plants, insects, other fish from Arctic and alpine environments, and the study of these proteins has contributed to advances in food preservation, cryogenic medicine, and the possibility of preserving organs for transplantation at much lower temperatures than currently possible. The extreme biology of Antarctica, in other words, has direct implications for human medicine and technology. The story of how not-athenoid fish came to dominate the Antarctic fish fauna is itself a remarkable piece of evolutionary history. Approximately 14 to 25 million years ago, as Antarctica cooled and the Southern Ocean became much colder, the fish that had previously lived in these waters faced an existential challenge: adapt to the cold or die. Most of the fish families that had lived in the region could not adapt quickly enough and went extinct locally. But one group, the not-athenoids, underwent an extraordinary radiation, evolving rapidly to fill the ecological niches left by the extinctions and developing a suite of adaptations, including the antifreeze proteins, that allowed them to thrive in the cold. Today, notothenoids account for the vast majority of fish species and fish biomass in the Southern Ocean, a dramatic example of what happens when a group of organisms is challenged by extreme environmental change and manages to meet that challenge. Now, having spent some time with the biology of Antarctica, let us turn to the geology, to the ancient history of the continent, written in stone and ice and mineral. Because Antarctica has a geological history that is, if anything, even more dramatic than its biological one, and it is a history that begins not with ice and cold, but with warmth and life. It is difficult to believe, looking at Antarctica today, that this continent was once covered in forests, but it was. The evidence is incontrovertible. Fossils of trees, of ferns, of flowering plants have been found in Antarctic rocks at multiple locations across the continent. Some of these fossils are quite young in geological terms, a few million years old, and they tell of a continent that, even as recently as the Pliocene, was warmer than today and supported at least sparse vegetation. But the most dramatic fossil discoveries go much further back. In the Transantarctic mountains, fossils of Glossopteris, a seed fern that was among the dominant plants of the ancient supercontinent Gondwana, have been found. These plants lived during the Permian period, approximately 250 to 300 million years ago, in a climate that was not tropical but was certainly far warmer than anything Antarctica experiences today. Robert Falcon Scott's Dying Polar Party, on their tragic return journey from the pole in 1912, actually collected geological samples that included Glossopteris fossils from a rock outcrop near the Beardmore Glacier, samples that they carried until their deaths, contributing to science even as their own lives slipped away. The significance of Glossopteris fossils in Antarctica extends beyond the climate story. It was the distribution of these fossils across multiple southern continents, Antarctica, South America, Africa, India, and Australia, that provided some of the most compelling early evidence for the theory of continental drift. When Glossopteris fossils were found on continents that are today separated by thousands of miles of ocean, the logical explanation was not that the seeds had somehow crossed those vast distances, but rather that the continents had once been joined together, that they had all been part of a single great landmass that had subsequently broken apart. That landmass was Gondwana, and its fragmentation over the past 180 million years is one of the great stories in the history of our planet. Antarctica was one of the last pieces of Gondwana to separate. For tens of millions of years after the initial fragmentation began, Antarctica remained connected to other southern continents, notably South America and Australia, by land bridges or at least by shallow seaways that allowed the exchange of species and the continuation of a broadly connected southern ecosystem. It was not until the opening of the Drake Passage, the gap between the southern tip of South America and the tip of the Antarctic Peninsula, approximately 30 to 34 million years ago, that Antarctica became truly isolated, surrounded on all sides by deep open ocean. The opening of the Drake Passage was a geological event of world historical consequence, though it unfolded over millions of years rather than in any human perceivable time frame. Once the passage opened, ocean water could circulate freely around the entire continent without being interrupted by land. This established the Antarctic Circumpolar Current, the largest ocean current on Earth, carrying more water than all the world's rivers combined, which effectively insulated Antarctica from the warmer ocean water to the north, preventing the northward flow of warm tropical water from reaching the southern continent. The result was glaciation. With the establishment of the circumpolar current, Antarctica cooled rapidly in geological terms, and the ice sheets that we associate with the continent today began to form. The East Antarctic ice sheet is thought to have reached approximately its current size by about 14 million years ago. The West Antarctic ice sheet is younger and more dynamic. And since the ice began to form, the continent has been in the grip of cold that has, at various points in the geological record, been somewhat less extreme than today, particularly during warm interglacial periods. but has never returned to the conditions of Gondwana, when trees grew near the South Pole and Antarctica was a fundamentally different place. The geological history of Antarctica is studied through a variety of means, and among the most fascinating of these is the use of zircon crystals as what geologists sometimes call time capsules. Zircon is an extraordinarily durable mineral. It is one of the hardest natural substances on Earth, resistant to the chemical and physical processes that destroy most other minerals over geological time. And crucially for geochronology, the science of determining the ages of rocks and geological events, zircon incorporates uranium into its crystal structure when it forms, but excludes lead. Since uranium decays to lead at a known rate, measuring the ratio of uranium to lead in a zircon crystal gives an extremely precise measurement of when that crystal formed. Zircon crystals found in Antarctic rocks have been dated to ages of over 3 billion years, making them among the oldest materials on Earth. These ancient zircons carry within them chemical signatures that preserve information about the conditions that existed when they formed, the temperature and pressure of the magma in which they crystallized, the chemical environment of that magma, and by extension, the type of geological event, volcanic eruption, crustal collision, deep crustal melting, that produced them. By collecting zircon crystals from rock outcrops across Antarctica, from the transantarctic mountains, from coastal exposures, from nunataks protruding through the ice, and dating them and analyzing their chemistry, geologists have been able to construct a remarkably detailed picture of the continent's deep history. They have identified ancient mountain-building events, collisions between tectonic plates that drove up mountains and fundamentally reorganized the geological structure of the continent. They have traced the connections between Antarctica and the other Gondwana continents, identifying the ancient sutures where plates collided and the ancient rifts where they pulled apart. And they have found evidence of geological events so ancient that they occurred when the only life on Earth consisted of single-celled organisms in a world utterly unlike anything we would recognize today. The picture that emerges from this work is of a continent with a geological history of extraordinary complexity and drama, a history that spans 4 billion years and includes episodes of mountain building, continental collision, rifting, glaciation, warming, and again glaciation. Far from being a static, changeless place, Antarctica has been one of the most dynamically active regions on the planet over geological time. The ice and cold that define it today are, from a geological perspective, a relatively recent development, a thin layer of recent history painted over a past of immense depth and variety. Let us now turn to the sounds of Antarctica, or more precisely, to the sounds that have been detected in and around Antarctic waters, sounds that have intrigued and puzzled scientists for decades, sounds that have occasionally been pressed into service by those who prefer dramatic explanations over scientific ones. The oceans of the world are full of sound. This is something that surprises many people who tend to think of the deep ocean as a world of silence. In fact, the ocean is constantly filled with noise, the creak and rumble of shifting sediments, the groaning of tectonic plates, the songs of marine mammals, the clicking of shrimp, the movement of currents over the seafloor. And occasionally there are sounds that stand out from this background noise because they are unusually loud, unusually structured, or simply hard to immediately explain. The most famous of these anomalous ocean sounds is the bloop. The bloop was detected in 1997 by the National Oceanic and Atmospheric Administration's Underwater Sound Surveillance System, a network of hydrophones originally designed during the Cold War to track submarines, subsequently repurposed for scientific monitoring. The bloop was an extraordinarily powerful low-frequency sound, audible across thousands of miles of ocean, with a character that initially suggested to some listeners that it might be biological in origin, that it had some of the qualities of a sound made by a living creature. The bloop immediately became the subject of intense speculation. Was it made by a creature so large that nothing in our current understanding of marine biology could account for it? Was it evidence of some enormous unknown animal lurking in the deep southern ocean? The internet, by 1997, just beginning to develop its capacity for enthusiastic speculation, embraced the bloop with considerable fervor. The actual explanation, when it was worked out in subsequent years, is simultaneously less dramatic and rather more interesting. The bloop, it turns out, was almost certainly the sound of an icequake, a large-scale fracturing event within an Antarctic ice shelf or glacier. When enormous masses of ice fracture and shift, they can produce sounds of extraordinary power and low frequency, sounds that can travel vast distances through the ocean. The specific signature of the bloop, when compared carefully to recordings of known icequakes, matched very well. The sound was real and impressive, but its source was geological rather than biological. This conclusion disappointed the monster hunters but delighted the glaciologists because it revealed something important about the acoustic behavior of Antarctic ice, about how the sounds generated by ice movement are transmitted through the ocean, and what those sounds can tell us about the dynamics of the ice sheet. It turned out that by carefully monitoring these sounds, scientists could learn things about ice shelf stability, about the rate and character of calving events where chunks of ice break off from the shelf, and ultimately about the health of the ice sheet itself. The upsweep is another anomalous oceanic sound that has received attention, though it is somewhat less famous than the bloop. First detected in 1991, the upsweep consists of a series of long, rising tones, sounds that sweep upward in frequency over the course of several seconds, hence the name. Unlike the bloop, the upsweep has continued to be detected intermittently ever since, which rules out a one-time event like a calving iceberg and suggests either a persistent source or a regularly recurring phenomenon. The origin of the upsweep is still not completely settled, but the leading hypothesis involves submarine volcanism, eruptions, or degassing events at underwater volcanic features in the Southern Ocean. The specific acoustic character of the upsweep is consistent with the sounds produced by volcanic processes under certain conditions, and the location from which the sound appears to originate aligns with areas of known submarine volcanic activity in the Southern Ocean south of New Zealand. Both the bloop and the upsweep illustrate an important principle. The ocean, and particularly the waters around Antarctica, produce a constant stream of sounds that carry genuine scientific information about geological and glaciological processes. The effort to understand these sounds, to catalog them, to identify their sources, to interpret what they tell us about the processes that generate them, is a legitimate and productive area of scientific research, and one that does not require any invocation of mysterious creatures or unknown civilizations. There is, however, a sound associated with Antarctica that is genuinely biological, genuinely mysterious in certain respects, and genuinely extraordinary in its character: the songs of the Antarctic blue whale. The Antarctic blue whale, Balænoptera musculus intermedia, is the largest subspecies of blue whale, which is itself the largest animal that has ever existed on Earth. Adult Antarctic blue whales can reach lengths of over 98 feet and weights of over 150 tons. They were hunted to near extinction during the 20th century, with an estimated 99% of the pre-whaling population eliminated between the 1900s and the 1970s. Current estimates put the Antarctic blue whale population at somewhere between 1,000 and 2,000 individuals, a fragment of what it once was, though the population appears to be slowly recovering since the prohibition on commercial whaling of blue whales took effect in the 1960s. These animals produce songs, long, complex sequences of low-frequency sounds that carry for hundreds, sometimes thousands of miles through the ocean. Blue whale songs are among the most powerful biological sounds on Earth, and they have been studied intensively both for what they reveal about the animal's behavior and social structure, and for what they reveal about the acoustic properties of the ocean. But there is something else remarkable about blue whale songs. They change, not just between individuals, but over time. Year by year, generation by generation, the songs of blue whales across different ocean basins have been gradually shifting in their characteristics, slowly deepening in frequency in some populations, changing in structure in others. Why this is happening is not fully understood, but it has been observed consistently across multiple ocean basins and multiple blue whale populations, and it raises fascinating questions about how these animals communicate, learn, and potentially coordinate behavior across the vast distances of the open ocean. We are now going to move to what is perhaps the most urgent and consequential area of Antarctic science, the subject of ice sheet stability and sea level rise, and specifically the story of the Thwaites Glacier. Because this is where Antarctica stops being simply a fascinating, remote continent full of interesting science and becomes directly, immediately relevant to the lives of billions of people living in coastal regions around the world. The Thwaites Glacier is a river of ice located in West Antarctica, draining from the interior of the continent into the Amundsen Sea. It is enormous, roughly the size of the state of Florida, and it is the most closely watched and carefully studied glacier in the world, for reasons that have everything to do with its remarkable instability and the potential consequences of that instability. Thwaites is sometimes called the Doomsday Glacier, a dramatic name, but one that glaciologists who tend toward understatement have not entirely resisted because the potential consequences of its collapse are genuinely sobering. The glacier currently holds enough ice to raise global sea levels by approximately 65 centimeters, roughly 2 feet, on its own. But that is not the primary concern. The primary concern is what Thwaites' collapse could trigger in its neighbors. Thwaites currently acts as a kind of cork or buttress for a significant portion of the West Antarctic ice sheet. It is positioned at the edge of a basin that contains ice equivalent to approximately 3 to 4 meters, roughly 10 to 13 feet, of sea level rise. The West Antarctic ice sheet is a marine ice sheet. It sits on bedrock that is, in many places, well below sea level, and it is held in place partly by the pressure of the ice at its margins, particularly by ice shelves like the Ross Ice Shelf and the smaller ice shelves at the edge of the Amundsen Sea. If those marginal ice shelves, and Thwaites Ice Shelf specifically, were to destabilize and collapse, the interior ice could follow, draining into the ocean far faster than it is currently doing. The process by which this could happen is called marine ice sheet instability, and it involves a feedback loop that once started may be difficult or impossible to stop. Here's how it works. Warm ocean water gets beneath an ice shelf and melts it from below. The ice shelf thins and retreats. As it retreats, the edge of the glacier, the grounding line, where the ice lifts off the bedrock and begins to float, retreats too. But because the bedrock beneath West Antarctica slopes downward toward the interior, each retreat of the grounding line exposes a taller wall of ice to the ocean. More ice is lost, more warm water gets in, and the process accelerates. In theory, once this process begins in earnest, it could continue until the entire marine-based ice sheet has drained, a process that could unfold over centuries but could also, under the right or wrong conditions, be faster. Understanding whether Thwaites is approaching this tipping point, and if so, how close it is one of the most pressing questions in all of contemporary Earth science. And to answer it, researchers have been conducting one of the most ambitious and technically challenging scientific investigations in the history of Antarctic research. At the heart of this investigation is the story of a remarkable machine, an autonomous submarine named Ran. Ran, named after the Norse goddess of the sea, is an autonomous underwater vehicle developed at the University of Gothenburg in Sweden. Unlike an ROV, which is tethered to a surface ship and operated by remote control, Ran is fully autonomous. It navigates by its own sensors, follows pre-programmed routes, makes its own decisions about how to handle the unexpected, and completes missions that would be impossible for any tethered vehicle operating in the complex, confined spaces beneath ice shelves. In January 2019, RAN was deployed beneath the Thwaites Glacier's ice shelf. This was a mission of extraordinary technical challenge. The ice shelf is moving, shifting, and unpredictable. The water beneath it is navigated by currents and thermal gradients that no sensor had ever measured there before. The seafloor is unmapped, and if anything went wrong, if RAN became trapped under the ice, or if its batteries failed, or if it navigated into a dead end from which it could not return, there was no way to rescue it. It was a one-shot mission, and losing RAN would mean losing not just a very expensive piece of equipment, but the scientific data it had collected. RAN completed the mission. Over the course of its deployment, it mapped hundreds of miles of the interface between the Thwaites ice shelf and the ocean water beneath it, measuring temperature, salinity, current speed and direction, and the topography of both the ice above and the seafloor below, building up a three-dimensional picture of the subshelf environment with a level of detail that had never before been achieved. What it found confirmed and extended the worst fears of the researchers. The data showed channels, pathways carved by flowing water into the underside of the ice shelf, through which warm circumpolar deep water was infiltrating far beneath the glacier, reaching areas that had been assumed to be protected from direct ocean melting. It showed that the melting was not uniform but highly structured, concentrated in specific zones where the geometry of the seafloor and the ice shelf created pathways for warm water to reach the most vulnerable areas. And it showed that the grounding line, the critical boundary where the glacier lifts off the bedrock, had retreated significantly since previous measurements, confirming that the process of marine ice sheet instability was not merely theoretical but actively underway. The results were published in scientific journals and attracted significant attention in the scientific community, because they painted a picture of a glacier that is changing faster than previous models had suggested, and in ways that make the prospect of a significant collapse in the coming centuries more rather than less plausible. Thwaites is not going to collapse tomorrow. It is not going to collapse this century, most scientists believe. But it is changing, and it is changing in ways that, if they continue, will have profound consequences for coastal communities everywhere. From the enormity of the Thwaites situation, let us shift to something that is visually more immediate, more striking, and in its own way just as scientifically fascinating: Blood Falls. Blood Falls is located at the terminus, the end of the Taylor Glacier, one of the valley glaciers that drains from the East Antarctic ice sheet into the McMurdo dry valleys. The dry valleys are themselves one of the most extraordinary environments in Antarctica, a series of deep valleys where the combination of low precipitation and strong, dry katabatic winds that pour down from the high plateau, keeps the valleys almost entirely free of snow and ice. The valleys are cold and dry enough that they bear a striking resemblance to the surface of Mars. Indeed, NASA has used them as a testing ground for Mars exploration equipment, because the conditions are about as close as you can get to Martian surface conditions on Earth. In this bizarre, Mars-like landscape at the foot of a glacier, there is a waterfall. Not a dramatic cataract, but a slow, oozing flow of liquid that emerges from a crack in the glacier's ice and runs down the ice face and onto the frozen surface of Lake Bonny below. And the liquid is red, not pink, not slightly rusty, genuinely, vividly red, the color of blood, enough to stain the white ice around it in a way that can be seen from considerable distance. The explanation for Blood Falls is a story that involves geology, chemistry, and biology in a combination that is almost novelistic in its elegance. Beneath the Taylor Glacier, sealed under the ice for approximately 1.5 to 2 million years, there is a reservoir of extremely unusual water. This water is what is called hypersaline. It contains salt concentrations roughly 3 to 4 times higher than normal seawater. Salt, as most people know, lowers the freezing point of water, and the water in this reservoir is so salty that it remains liquid at temperatures well below the normal freezing point. It is also rich in iron that came from the bedrock over which the water flowed during the long period of its isolation. And because this reservoir has been sealed from the surface, it has been sealed from oxygen as well. The water is anoxic, essentially oxygen-free. When this ancient hypersaline, iron-rich, oxygen-depleted water finds a pathway to the surface through cracks in the glacier ice, it does what iron-rich water always does when it meets oxygen. The iron oxidizes, it rusts. And rusted iron is red, the same chemical process that makes rust red makes blood falls red. The waterfall is running water stained the color of blood by the oxidation of iron that has been locked underground in the dark for millions of years. But the story of blood falls is not just geological. That ancient, sealed reservoir is also home to a microbial ecosystem, a community of bacteria that has been living in that cold, dark, salty, oxygen-free environment for an enormous span of time. These bacteria have no sunlight. They have no oxygen in the conventional sense. They have survived by developing metabolic pathways that use sulfate as an electron acceptor instead of oxygen, essentially breathing sulfate instead of oxygen in a process called anaerobic sulfate reduction. They cycle iron and sulfur through a complex chemical dance that sustains the entire community, and they have been doing this in isolation for hundreds of thousands to millions of years. These bacteria have become important model organisms for scientists studying the possibility of life on other worlds. Mars, we now know, has subsurface water, kept liquid by the pressure and salt content of the rocks above it, in conditions remarkably similar to those beneath Taylor Glacier. If bacteria can survive for millions of years in the Blood Falls Reservoir, doing chemistry that requires no sunlight and no oxygen, then it is not unreasonable to ask whether similar organisms might survive in similar conditions on Mars, or on the ice-covered moons of the outer planets, or in any of the countless other environments in the solar system where liquid water and chemical energy sources are potentially available. Blood Falls, in other words, is not just a beautiful and strange feature of the Antarctic landscape. It is a window into one of the most fundamental questions in astrobiology. Are we alone? Let us now talk about an environment that in some ways parallels the sub-ice ecosystems of Antarctica, even though it is geographically about as far from the southern polar region as it is possible to get. In a salt mine in Romania, the Moval Cave system, scientists have discovered an ecosystem that, like the ecosystems under Antarctic ice shelves, has been isolated from the surface world for millions of years and has developed entirely without sunlight. The Moval Cave was discovered by accident in 1986 during construction work near the Black Sea coast of Romania. Workers drilling into the ground unexpectedly broke through into a cave system that had been sealed from the surface for an estimated 5 million years. The air inside the cave is toxic by normal standards, high in carbon dioxide and hydrogen sulfide, low in oxygen. The water is warm and sulfurous, and yet the cave is full of life. Approximately 50 animal species have been identified in Moval Cave, all but a few of them completely unknown to science before the cave's discovery. There are spiders and centipedes and isopods, small crustaceans and leeches, all of them living in permanent darkness, all of them supported by a food web that begins not with photosynthesis but with chemosynthesis, with bacteria that harvest energy from the hydrogen sulfide in the cave water and use it to build organic molecules. These bacteria form mats on the surface of the cave water, and the animals graze on these mats, and other animals eat those animals, building up a complete and self-sustaining ecosystem that has run entirely on chemical energy for 5 million years. Why does this matter for Antarctica? Because the parallels are striking and illuminating. Moval Cave and the Blood Falls Reservoir are very different environments. One is a terrestrial cave, the other is a subglacial lake system. but they share fundamental characteristics: isolation from the surface world, reliance on chemical rather than solar energy, extreme conditions by normal biological standards, and the existence, despite all of that, of complex and diverse communities of living organisms. Each of these systems reinforces the lesson of the others. Life does not require sunlight. Life does not require moderate temperatures. Life does not require oxygen. What life requires, at minimum, is liquid water and a source of chemical energy, and both of those are far more widely available in the universe than we once thought. We are now approaching the end of the first part of our exploration of Antarctica, and I want to step back for a moment and reflect on what we have covered so far and what it all adds up to. We began with the myths and conspiracy theories that surround Antarctica, and we found that while the specific claims of these theories almost never hold up to scrutiny, they are pointing, however imperfectly, at something real. The genuine mystery and inaccessibility of this continent, the genuine existence of things there that most people have never heard of and would find astonishing if they knew about them. We explored the geological history of the continent, the ancient Gondwana supercontinent, the opening of the Drake Passage, the formation of the Antarctic circumpolar current, and the glaciation that followed. We looked at the ancient zircon crystals that carry within them memories of geological events billions of years in the past. We contemplated what it means that this continent, which is now the coldest and most ice-covered place on Earth, was once forested, once warm, once home to animals and plants of kinds that no longer exist. We spent time with the extraordinary biology of Antarctica, the antifreeze proteins of the not-athenoid fish, the remarkable adaptations of Antarctic octopuses, the astonishing discovery of corals and sponges, and sea spiders thriving in the darkness beneath ice shelves. We visited Blood Falls and the subglacial reservoir beneath Taylor Glacier, where bacteria have been cycling iron and sulfur in the dark for millions of years. We connected these discoveries to the broader question of where life can exist in the universe. We listened to the sounds of the Antarctic Ocean, the Bloop and the Upsweep, the songs of blue whales, and found in them both natural explanations and genuine scientific insight. We went aboard the autonomous submarine RAN as it made its lonely journey beneath the Thwaites Glacier, mapping the pathways through which warm water is eating at the ice from below, building a case for a future that coastal communities everywhere will need to reckon with. And through all of this, one theme has emerged with increasing clarity. Antarctica is not simply a remote and frozen wasteland. It is a place of extraordinary complexity, extraordinary history, and extraordinary importance. What happens in Antarctica does not stay in Antarctica. The processes underway in this continent, the melting of ice sheets, the behavior of ocean currents, the evolution of extreme biological adaptations, the preservation of Earth's atmospheric history in ancient ice, are connected to the life and future of the entire planet in ways that we are only beginning to understand. In the second part of our exploration, we will go deeper. We will spend more time with the sub-ice ecosystems, looking more closely at what we know and don't know about the creatures that live in these extreme environments. We will investigate the dry valleys more fully and explore what they tell us about the limits of habitability on Earth and other worlds. We will return to the ice sheet stability question and examine what scientists are doing to monitor and understand the changes underway. We will look at the astronomical and atmospheric research conducted from Antarctic research stations and at what it has contributed to our understanding of the cosmos. And we will end, as perhaps we should, with a reflection on what Antarctica means not just as a scientific subject, but as a place, a presence, a reminder of how much of this extraordinary world we have yet to understand. The ice is speaking. The question is whether we are listening closely enough to hear what it is saying. Stay with us. Before we close out the first half of our journey, there is one more dimension of Antarctica we should explore, one that weaves through everything else we have discussed and gives it additional depth. This is the question of the continent's atmosphere, and specifically what the atmosphere above Antarctica can tell us about both the history and the future of our planet. Antarctica is home to one of the most important long-term atmospheric monitoring programs in the history of science. The ice cores drilled from the East Antarctic ice sheet, particularly from sites near the Russian Vostok station, the European Project for Ice Coring in Antarctica, EPICA, site at Dome Sea, and several other locations, have yielded records of atmospheric composition stretching back over 800,000 years. These records, preserved in the tiny air bubbles trapped within the ice as each year's snowfall was compressed and consolidated, allow scientists to measure the concentration of greenhouse gases, carbon dioxide, methane, nitrous oxide, at any point over the past 8 centuries of millennia with remarkable precision. What these records show is, on one level, reassuring. The planet has experienced dramatic swings in greenhouse gas concentrations and temperatures many times in the past, and it has always recovered. Ice ages have come and gone. Warm periods have followed cold ones. The geological history of climate is one of constant change, not stability. But on another level, what the ice cores show is deeply sobering. The concentration of carbon dioxide in the atmosphere over the past 800,000 years has oscillated between roughly 180 parts per million during glacial periods and roughly 280 parts per million during interglacial warm periods. This range, this oscillation, appears to represent the natural range of variation in atmospheric CO2 under the conditions that have prevailed for the past several 100,000 years. And the current concentration of CO2 in the atmosphere, which is now well above 400 parts per million, a level not seen in at least 800,000 years and possibly considerably longer, is, by this historical standard, extraordinary. The ice cores cannot tell us exactly what the consequences of this extraordinary concentration will be. The planet has not experienced such conditions in the period of recorded human history, or even in the period for which we have written records. We are, in a meaningful sense, moving into uncharted territory. But the ice cores can tell us how the climate responded to much smaller changes in greenhouse gas concentrations in the past, and by extension, they can help us build and calibrate the models that we use to project future climate change. In this sense, the ancient air bubbles in Antarctic ice are not merely historical artifacts. They are data, hard data, that feeds directly into our best current understanding of where the climate is heading. The story of how the ice cores were drilled, processed, and analyzed is itself a remarkable one. Drilling an ice core from the Antarctic ice sheet is an extraordinarily delicate operation. The drill must go straight down for thousands of meters, through ice that is under enormous pressure and that is constantly, slowly moving. The core that comes up must be handled with extreme care. It is fragile, it is cold, and any contamination with modern air will invalidate the ancient air bubble data that makes the core scientifically valuable. The cores are then cut into sections and analyzed by teams of scientists from multiple countries, working in cold rooms that keep the ice from melting while they extract their samples. The EPICA Dome Sea core, drilled to a depth of approximately 3.27 kilometers, currently holds the record for the oldest directly measured atmospheric data from any source. The air in the deepest portions of this core was trapped approximately 800,000 years ago. But Antarctic glaciologists are now working on a project known as Beyond EPICA, or Oldest Ice, that aims to recover ice from a location where the ice is thick enough and the local conditions right enough that the ice at the bottom of the sheet may be over 1 million years old. If successful, this project would extend the direct atmospheric record back through a period that is scientifically crucial. The point at which the rhythm of ice ages shifted from 41,000-year cycles to 100,000-year cycles, a transition known as the mid-Pleistocene transition, whose causes are still not fully understood. What is in that ancient ice? What did the atmosphere look like 1 million years ago, and how does knowing that help us understand the climate dynamics of the deep past? These are questions that Antarctic ice scientists are working with extraordinary care and patience to answer. One more piece of the Antarctic puzzle deserves attention before we move into the second half of our exploration. The extraordinary phenomenon of the polar vortex and the ozone hole, two features of the Antarctic atmosphere that have, in very different ways, shaped our understanding of how the planet's atmosphere works and how human activities can affect it. The Antarctic ozone hole, the dramatic seasonal depletion of stratospheric ozone above Antarctica that was first scientifically documented in the 1980s, is one of the most significant environmental discoveries of the 20th century. Stratospheric ozone, concentrated in a layer of the atmosphere approximately 15 to 35 kilometers above the Earth's surface, absorbs a large proportion of the sun's ultraviolet radiation. Without this ozone layer, UV radiation at the Earth's surface would be dramatically higher, with severe consequences for biological systems, including, crucially, for the marine phytoplankton that form the base of the Southern Ocean food web. The discovery that a hole, not a literal hole, but a region of dramatically reduced ozone concentration, was forming over Antarctica each spring was initially greeted with skepticism. The measurements showing the depletion were so dramatic that scientists initially assumed there was something wrong with their instruments. But the measurements were confirmed, the mechanism was worked out, chlorofluorocarbon compounds released into the atmosphere were being broken down by sunlight to release chlorine, which catalytically destroyed ozone in reactions that were particularly efficient in the polar stratosphere during winter and spring. And the scientific and policy response that followed represents one of the genuine success stories in the history of environmental regulation. The Montreal Protocol, signed in 1987, phased out the production of ozone-depleting substances, and today the ozone hole is slowly recovering, expected to return to pre-depletion levels sometime around the middle of this century. The polar vortex is related but distinct. It is a large area of low pressure and cold air surrounding the polar region, maintained in winter by the temperature differential between the pole and lower latitudes. In the southern hemisphere, the Antarctic polar vortex is particularly strong and stable. In fact, its stability was one of the factors that made the ozone hole so severe, because the cold temperatures within the vortex facilitated the formation of polar stratospheric clouds on which the ozone-destroying reactions took place. But the polar vortex also has effects closer to the ground. When the stratospheric vortex is disrupted, when warm air from lower latitudes breaks through into the polar stratosphere, it can influence weather patterns thousands of miles away. The dynamics of the polar vortex, both in the north and south, have become an increasingly important area of atmospheric research as scientists work to understand how changes in the polar atmosphere connect to weather patterns across the broader globe. Antarctica, the more you look at it, the more it reveals. Every question you ask opens onto three more. Every discovery raises new puzzles. Every expedition comes back with data that confirms some hypotheses, upends others, and generates new questions that will take decades to answer. And that is ultimately what makes this continent so endlessly, compellingly fascinating. Not the conspiracy theories, though we have given them a fair hearing. Not the legends, though some of them are genuinely evocative, but the reality. The actual documented, scientifically established reality of a continent that is simultaneously ancient and dynamic, frozen and alive, remote and crucially relevant, strange beyond imagination, and yet the more you study it, somehow familiar, a piece of our planet, a record of our planet's past, and a window onto our planet's future. We have covered an enormous amount of ground in this first part of our journey, and yet we have barely begun. The dry valleys await us, with their Mars-like landscapes and their stubborn, improbable microbial life. The full story of the sub-ice biological communities is still to be told. The astronomical discoveries made from Antarctic research stations have yet to be explored. The complete story of the Thwaites Glacier and what it means for the future of coastlines everywhere needs its final chapters. And there are discoveries so recent that scientists are still working to understand their implications. All of that is coming. In the second part of our exploration, we will go deeper into the ice, deeper into the science, deeper into the mystery. Antarctica has kept its secrets for a long time. We are only just beginning to unlock them. Thank you for joining us for the first part of this extraordinary journey. If you have been watching and listening along, we would love to know where in the world you are and what time it is for you. The community of people who care about these stories, who find in the science of this distant continent a reflection of some of our deepest questions about life and the universe, spans the entire globe. Leave a comment, let us know you are there, and make sure you are subscribed so that you do not miss the second part of this exploration. Antarctica is waiting. Welcome back. If you are joining us for the first time, you have arrived at the second half of what has been, I hope, an extraordinary journey into the most remote, the most mysterious, and the most scientifically consequential continent on the face of our planet. And if you have been with us since the beginning, then you already know that Antarctica is a place where reality consistently outpaces imagination, where the actual, documented, scientifically established truth is more astonishing than almost anything the conspiracy theorists or the legend makers have managed to conjure. In the first part of our exploration, we covered the myths and the legends and the conspiracy theories, and we examined them honestly. We traced the geological history of Antarctica from its origins as part of the ancient supercontinent Gondwana through the opening of the Drake Passage and the formation of the ice sheets that define the continent today. We listened to the sounds of the Antarctic Ocean. We visited Blood Falls and marveled at the ancient bacteria living in their sealed, sunless, oxygen-free reservoir beneath Taylor Glacier. We went beneath the Thwaites Glacier with the autonomous submarine ran and confronted the sobering reality of what is happening to that enormous mass of ice. And we breathed the ancient air preserved in Antarctic ice cores, air that carries within it a chemical record of our planet's atmospheric history stretching back 800,000 years. Now we go deeper. We are going to spend more time with the biology of the extreme, with the creatures that have found ways to live in conditions that should, by any reasonable measure, be fatal. We are going to explore the McMurdo dry valleys in detail, one of the most extraordinary environments on Earth, and consider what they tell us about the possibility of life on other worlds. We are going to look at the oceanography of the Southern Ocean, the currents, the upwellings, the extraordinary food webs, and understand why this remote body of water is one of the most biologically productive and climatically important ocean systems on the planet. We are going to explore the astronomical discoveries made from the ice and the atmospheric science that has changed our understanding of the planet. And we are going to confront, honestly and seriously, the question of what the future of Antarctica looks like, what is changing, how fast, and what it means for the rest of us. This is part 2 of the story of Antarctica. Let us begin. We ended the first part of our journey at a point of reflection, a moment of stepping back and considering what Antarctica means, not just as a scientific subject, but as a presence in the human imagination. And that reflection leads naturally into a question that has been implicit in everything we have discussed, but not yet directly addressed. Why do we care? Why does Antarctica matter to people who will never go there, who live thousands of miles from its shores, whose daily lives seem utterly disconnected from the ice and cold and darkness of the southern polar region? The answer, it turns out, is everywhere you look. Antarctica is not a distant irrelevance. It is, in ways both direct and subtle, woven into the fabric of the world that all of us inhabit. The ice sheets of Antarctica contain enough water to raise global sea levels by approximately 58 meters, roughly 190 feet, if they were to melt entirely. That is not going to happen tomorrow, or this century, or probably even this millennium. But even partial melting, the melting that is already underway, that has already raised sea levels measurably, and that will continue to do so over the coming decades and centuries, has direct consequences for coastal communities, for island nations, for river deltas and ports and beaches and wetlands all over the world. The Antarctic Circumpolar Current, that enormous river of water flowing endlessly around the continent, plays a crucial role in the global ocean circulation system, distributing heat and nutrients around the world's oceans in ways that affect climate and marine productivity on every shore. The deep, cold, oxygen-rich water that forms in the Southern Ocean and sinks to the bottom of the world ocean, a process called Antarctic bottom water formation, ventilates the deep ocean, maintaining the oxygen levels that deep sea life depends on and driving a component of the global thermohaline circulation that affects climate patterns worldwide. The ozone layer above Antarctica, the recovery of which we discussed in the first part, affects the amount of ultraviolet radiation reaching not just the southern polar region, but the entire southern hemisphere. The atmospheric chemistry happening in the Antarctic stratosphere is connected to chemistry happening in the atmosphere everywhere else. The ice cores that preserve 800,000 years of atmospheric history provide data that is fundamental to our understanding of the climate system, data that informs not just academic research but the models and projections that guide policy decisions. And the biology, the extraordinary, improbable, resilient biology of Antarctica, is teaching us things about the nature of life itself that have implications far beyond the continent. The antifreeze proteins of Antarctic fish have medical applications. The chemosynthetic bacteria of subglacial environments are expanding our understanding of where life can exist in the universe. The evolutionary history of Antarctic organisms is a unique and irreplaceable record of how life adapts to extreme environmental change. Antarctica matters. It matters enormously. And the more we study it, the more we realize how much we did not know and how much we still have to learn. Let us now spend some time in the McMurdo dry valleys because they deserve a full and careful exploration. We mentioned them briefly in the first part, the Mars-like landscapes, the extreme dryness, the strangeness of a place in Antarctica that is almost entirely free of snow and ice. But the dry valleys are so extraordinary and so scientifically important that they warrant considerably more attention. The McMurdo dry valleys are located in the Transantarctic Mountains, west of McMurdo Sound, and they encompass approximately 4,800 square kilometers, roughly 1,850 square miles. They consist of a series of broad, flat-bottomed valleys carved by ancient glaciers and now largely free of ice, protected from snow accumulation by the strong katabatic winds that pour down from the polar plateau. These winds are so dry and so powerful that any snow that falls in the valleys is quickly sublimated, converted directly from solid ice to water vapor, bypassing the liquid state entirely before it can accumulate. The result is a landscape that is genuinely alien. The valley floors are covered with coarse, angular rocks and gravel material left behind by ancient glaciers, sorted and resorted by millennia of freeze-thaw cycling. There is almost no visible life. No plants, no animals, nothing that would catch the eye of a casual observer as clearly biological. The landscape is brown and gray and in the winter deeply, absolutely dark. Temperatures drop to -30 or -40 degrees Celsius. Winds howl. It is, by most conventional measures, one of the most inhospitable places on the surface of the earth. And yet the dry valleys are teeming with life. You just have to know where to look. The valleys contain several lakes, permanently ice-covered lakes, sealed under a layer of ice several meters thick that never melts even in the Antarctic summer. The most studied of these are Lake Vonda, Lake Bonny, at whose shore Blood Falls emerges, as we discussed, Lake Hoare, and Lake Fryxell. Each of these lakes has its own distinctive chemistry and its own distinctive biological community, shaped by the particular conditions of temperature, salinity, chemistry, and light penetration that characterize each lake. Lake Vonda is particularly remarkable. It is stratified into distinct layers of water with very different properties, a phenomenon called meromictic stratification, which occurs when the lower layers of water are so dense, because of high salt concentration or high temperature, that they do not mix with the layers above even under the stirring action of wind and seasonal temperature changes. The bottom water of Lake Vonda is actually quite warm, reaching temperatures of approximately 25 degrees Celsius or 77 degrees Fahrenheit, despite the fact that the lake's surface is permanently frozen. This warmth comes from a combination of solar heating. Sunlight penetrates through the clear ice cover and is absorbed by the saline lower layers, which do not lose heat by convection because they cannot mix with the cooler, fresher water above, and possibly some geothermal input from below. The biology of Lake Vonda is correspondingly unusual. Microbial mats, complex communities of microorganisms living in a stratified, laminated structure, are found at various depths in the lake, adapted to the specific conditions of temperature, light, and chemistry at each level. Some of these organisms photosynthesize using the dim light that filters down through the ice cover. Others use chemical energy sources. Together, they form an ecosystem of remarkable complexity and considerable antiquity, a system that has been running in various forms for thousands of years in isolation from the rest of the world. But the most extraordinary biology in the dry valleys is not in the lakes. It is in the rocks. Endolithic organisms that live inside rocks, are found throughout the dry valleys, sheltering within the porous interior of translucent rocks like quartz sandstone and granite. These organisms, mostly photosynthetic algae, cyanobacteria, and fungi, find in the rock interior a microenvironment that is significantly more hospitable than the rock's surface. The rock provides physical shelter from the wind. It moderates temperature fluctuations, preventing the extreme swings between day and night and between seasons that characterize the exposed surface. And crucially, translucent rock transmits enough light for photosynthesis while blocking enough UV radiation to prevent the kind of photo damage that would kill exposed organisms. To find endolithic communities, you have to break open the rocks. Inside, just below the translucent outer surface, there is a thin band of color, green or green-gray, or sometimes reddish, that is the visible signature of the biological community. This band, typically just a few millimeters thick, contains a surprisingly complex assemblage of organisms. The primary producers, the photosynthetic algae and cyanobacteria, heterotrophs that consume the organic material produced by the photosynthesizers, and fungi that form partnerships with algae in the kinds of associations we call lichens. These communities grow extraordinarily slowly. The rate of biomass production in endolithic communities in the dry valleys has been estimated at rates so low that the communities may accumulate only a fraction of a millimeter per decade. Individual organisms may live for thousands of years, growing so slowly that the change is imperceptible on any human timescale. And yet they are alive, they are metabolically active. They are doing the fundamental things that living organisms do, harvesting energy, building organic molecules, reproducing, evolving. The endolithic communities of the dry valleys have attracted enormous scientific attention for a reason that goes well beyond Antarctica. They represent what may be the absolute minimum conditions under which life based on photosynthesis can exist. They are pushed to the very edge of viability, surviving in conditions that are just barely sufficient, just barely enough light, just barely enough moisture, just barely enough warmth during the brief Antarctic summer to sustain life. And the fact that they survive at all tells us something profound about the resilience and adaptability of life as a phenomenon. It also tells us something about Mars. The surface of Mars today is cold, dry, and bombarded by ultraviolet radiation, because Mars lacks the ozone layer that shields Earth's surface. Sound familiar? The conditions on Mars are in broad terms not entirely unlike the conditions in the dry valleys, though Mars is colder, drier, and more radiation intense than even the most extreme dry valley environment. But if life can survive in the rocks of the dry valleys, the question of whether life might have survived, or might even still survive, in rocks on Mars becomes genuinely interesting. If there is or was any life on Mars, it might be or might have been hiding inside rocks, using them as shelter and light filter, living at rates so slow that detecting it would require extraordinarily sensitive instruments. The dry valleys have taught us that looking for life on Mars by scanning the surface visually is probably not the right approach. Life that has retreated into rocks to survive is not going to be visible from orbit. Finding it would require drilling, breaking open rocks, using biochemical detection methods. And that is influencing the design of future Mars exploration missions in ways that are directly traceable to the discoveries made in this extraordinary Antarctic landscape. Now let us move from the land to the sea, because the Southern Ocean, the body of water that surrounds Antarctica and is sometimes called the world's most important ocean, is a subject that deserves careful and detailed attention. The Southern Ocean is not merely the backdrop against which Antarctic science takes place. It is one of the primary drivers of global climate, one of the most biologically productive ocean systems on Earth, and one of the fastest changing marine environments on the planet. The Southern Ocean is defined by the Antarctic circumpolar current, which we have already discussed, but its character is shaped by much more than that single dominant circulation feature. It is a place of extraordinary physical violence. The seas around Antarctica are among the roughest in the world, driven by the same strong westerly winds that circle the globe unimpeded by any land in the southern latitudes, building waves of enormous size and power. The waves of the Southern Ocean are legendary among sailors, and the tales of ships caught in their violence, ships that were built to be strong and were still broken, are among the most terrifying in maritime history. But beneath the violent surface, something remarkable is happening. The Southern Ocean is one of the most productive biological systems on Earth, and the key to that productivity is a process called upwelling. Upwelling occurs when surface waters are pushed away from an area by winds, by ocean currents, by the dynamics of circulation around the continent, and deep water rises to replace them. The deep water that rises in the Southern Ocean is not just cold and dense. It is also rich in nutrients, phosphate, nitrate, silicate, and iron that have accumulated over centuries as organic material from the surface layers has sunk and decomposed. When this nutrient-rich deep water rises to the sunlit surface zone, it fertilizes explosive growth of phytoplankton, the microscopic, photosynthetic organisms that form the foundation of the ocean food web. Antarctic phytoplankton, during the summer months when sunlight is abundant and upwelling nutrients are plentiful, can grow so densely that they change the color of the surface water, turning it green or blue-green in visible satellite imagery. This bloom of phytoplankton supports everything else in the Southern Ocean food web: the zooplankton that graze on the phytoplankton, the krill that feed on the zooplankton, the fish and squid that feed on the krill, and the spectacular megafauna, the whales, the seals, the penguins that feed on the fish and squid and krill. Antarctic krill, Euphausia superba, is perhaps the most ecologically important single species in the Southern Ocean, and possibly one of the most important in any ocean ecosystem on Earth. These small crustaceans, averaging about 2 inches in length, exist in quantities that are almost beyond comprehension. The total biomass of Antarctic krill has been estimated at somewhere between 300 million and 500 million tons, making it one of the most abundant animal species on the planet. These krill aggregate in dense swarms that can cover hundreds of square kilometers and extend many meters deep, swarms so dense that they can be detected by ship sonar and seen from space. Almost everything in the Southern Ocean ecosystem depends, directly or indirectly, on krill. Blue whales, fin whales, humpback whales, minke whales, all of the great baleen whales of the Southern Ocean consume vast quantities of krill during the Antarctic summer, building up the fat reserves they need to sustain themselves during migration and breeding season. Craybaiter seals, the most abundant seal species in the world, with a population estimated at perhaps 15 million individuals, have evolved specialized teeth that act as sieves, allowing them to filter krill from the water. Chinstrap penguins, macaroni penguins, and Adelie penguins all depend heavily on krill. Antarctic fur seals, leopard seals, numerous species of seabirds, the list goes on. The krill-centered nature of the Southern Ocean food web makes it both extraordinarily productive and extraordinarily vulnerable. If krill populations decline, whether because of changes in sea ice extent, krill depend on sea ice for shelter and as a source of ice algae that they graze on, changes in ocean temperature, changes in the upwelling of nutrients, or direct exploitation by commercial fisheries, the consequences ripple through the entire system. Everything that depends on krill is affected. And because many of the things that depend on krill are themselves ecologically important, the great whales, for instance, whose dying bodies sink to the seafloor and provide nutrients to deep-sea communities in a process called whale fall, the consequences of krill decline can cascade in unexpected directions. The great whales of the Southern Ocean deserve their own moment of attention, because their story is one of the most dramatic and sobering chapters in the history of human interaction with the natural world. And their potential recovery is one of the most important ecological stories being told today. Before the age of industrial whaling, before factory ships and explosive harpoons made it possible to catch whales faster than the populations could replace themselves, the Southern Ocean supported whale populations of staggering abundance. Blue whales, fin whales, sei whales, right whales, sperm whales, humpback whales, these animals existed in numbers that modern observers can barely imagine. The southern seas were, in the accounts of early explorers and sailors, full of whales, full of them. Leaping, breaching, spouting, blowing, enormous animals everywhere, in numbers that seemed inexhaustible. They were not inexhaustible. In the space of roughly 70 years, from around 1900 to 1970, industrial whaling in the Southern Ocean killed approximately 2 million whales. 2 million. The populations of virtually every large whale species in the Southern Ocean were reduced by anywhere from 60 to 99%. The blue whale, the largest animal that has ever lived on Earth, was reduced to perhaps 1% of its pre-whaling abundance. The right whale, so named because it was the right whale to catch, being slow, floating when dead, and rich in oil, was essentially exterminated from large parts of its former range. The consequences of this slaughter extended far beyond the whale populations themselves. Whales, as we have already touched on, are not simply passive consumers of krill. They are active participants in the ocean ecosystem, recycling nutrients through their feeding and excretion. They dive deep to feed and come to the surface to breathe and defecate, bringing nutrients from the deep ocean up to the sunlit surface zone in what oceanographers call the whale pump. They carry iron, a critical limiting nutrient for phytoplankton growth in the Southern Ocean, in their bodies from feeding grounds to breeding grounds, effectively transporting iron over enormous distances. And when they die, their bodies sink to the seafloor and provide a concentrated, long-lasting food source for deep-sea communities, communities that in turn process the organic material and return the nutrients to the water column. Remove 2 million whales from this system, and you have not merely removed 2 million large animals. You have disrupted a set of ecological processes, nutrient cycling, iron transport, deep-sea nutrition, phytoplankton fertilization, that the entire ocean ecosystem was built around. The Southern Ocean that exists today is, in important respects, a diminished version of what it was before whaling, a system running at reduced capacity, because one of its most important functional components has been so drastically reduced. The good news, and there genuinely is good news here, is that some of the whale populations are recovering. Humpback whales, whose Southern Ocean population was reduced from perhaps 100,000 individuals to around 1,500 by the height of whaling, have recovered dramatically since commercial whaling ended, and current estimates put the Southern Ocean humpback population at perhaps 40,000 to 60,000 animals, still below pre-whaling levels, but a remarkable recovery nonetheless. Some populations of fin whales and minke whales are also recovering. The blue whale's recovery is slower and more uncertain, partly because their populations were so severely reduced, and partly because their slow reproductive rate, females give birth to a single calf every 2 to 3 years, means that recovery takes many generations. As whale populations increase, oceanographers are beginning to detect changes in the Southern Ocean ecosystem that appear to reflect the recovering whale pump, subtle changes in nutrient distribution, and phytoplankton productivity in areas where whale populations are recovering most strongly. The ocean is slowly rebuilding itself. The process will take decades, probably centuries, to complete, but it is happening. Now let us go back beneath the ice, because we left the sub-ice shelf communities at a point of genuine scientific excitement, the discovery of corals and sponges and octopuses thriving in the dark beneath the Filchner and other ice shelves, and there is considerably more to say about what these communities are telling us and how scientists are working to understand them. The fundamental puzzle of sub-ice shelf communities is the energy question. All complex ecosystems, all ecosystems involving animals rather than just microbes, ultimately depend on a source of organic carbon, of biological fuel that sustains the food web. In most marine ecosystems, that fuel comes from photosynthesis. Sunlight drives phytoplankton growth, phytoplankton fuel zooplankton, zooplankton fuel larger animals, and so on. But beneath an ice shelf, sunlight does not penetrate. The ice above is thick enough to block virtually all light. So there is no photosynthesis. Where is the organic carbon coming from? Several mechanisms have been proposed, and the scientific consensus at the moment is that the answer is probably a combination of all of them, with different mechanisms being more or less important in different locations and under different conditions. The first and most straightforward mechanism is physical transport. In the Southern Ocean, there are complex current systems operating within and around ice shelf cavities. Some of these currents flow into the cavity from the open ocean, and they carry with them particulate organic matter, dead phytoplankton, fecal pellets, fragments of various organisms that has been produced in the sunlit outer ocean. This material, sometimes called marine snow, because of the way it drifts slowly downward through the water column, can travel considerable distances under the ice before finally settling to the seafloor. For communities near the edges of ice shelves, where the distance from open water is relatively short and the currents relatively strong, this mechanism might supply enough organic material to sustain significant animal communities. But for communities deep under ice shelves, like the sponges found on that boulder 160 miles from open water under the Filchner ice shelf, the transport mechanism seems insufficient. The dilution and decomposition of organic material over 160 miles of ice-covered water, against the background of extremely low production in those waters, would seem to leave very little fuel for a community of filter-feeding sponges at that distance from open water. So something else must be going on. The second mechanism is chemosynthesis. As we discussed in the context of Blood Falls and the Mouville Cave, certain bacteria can produce organic carbon using chemical energy rather than sunlight specifically, by oxidizing reduced chemical compounds like hydrogen sulfide, methane, or iron. If there are sources of these chemical energy compounds in the sub-ice shelf environment, and given the geological diversity of the Antarctic seafloor, there may well be, then chemosynthetic bacteria could form the base of a food web that is entirely independent of sunlight. This is exactly what happens at deep-sea hydrothermal vents and cold seeps, which support diverse and often abundant animal communities despite being far below the reach of sunlight. The third mechanism is something more exotic and unexpected, the ice itself. Research has shown that the underside of sea ice, and possibly the underside of ice shelves as well, can support communities of ice algae, photosynthetic organisms adapted to grow in the extreme low light conditions just beneath the ice. In sea ice, these ice algae communities are well documented and play an important role in the ecology of Antarctic waters, including providing food for krill that scrape the algae from the underside of the ice. Whether similar communities exist on the underside of ice shelves, where the ice is much thicker and the light levels correspondingly much lower, is an open and actively debated question. What is becoming increasingly clear as the research accumulates is that the ecosystems beneath Antarctic ice shelves are not simply poor, stressed versions of the communities found in better lit, better supplied open water environments. They are distinctive communities, adapted to their specific conditions in ways that are only beginning to be understood, with ecological structures and energy pathways that differ in fundamental ways from those of surface water ecosystems. Consider the sponges. The sponges found under the Filchner ice shelf are not just any sponges. They are specific species, adapted to the extreme conditions of cold, darkness, and limited food supply. Some of them are thought to be extraordinarily slow-growing, adding only fractions of a millimeter per year to their body size, conserving every calorie with an efficiency that would be remarkable in any organism. Some of them appear to be extremely long-lived, potentially reaching ages of hundreds or even thousands of years. And their community structure, the way they are arranged on the seafloor, the relationships between different species, appears to be organized around principles that differ from those of more conventional marine communities. The discovery of stationary filter feeders in these locations has opened up a broader question about the distribution of animal life in sub-ice environments. If sponges can survive under the Filchner ice shelf 160 miles from open water, what else might be living there? Mobile animals, animals that can move through the water column in search of food, might be even better positioned to exploit whatever food sources exist in these environments. ROV surveys conducted in ice shelf cavities at various locations around the continent have turned up a variety of mobile animals, fish, squid, various invertebrates. The diversity seems to increase closer to the ice shelf edges, where connections to the open ocean food web are stronger, but mobile animals have been found at substantial distances from the edge as well. The octopuses found in sub-ice shelf environments are particularly interesting in this regard. Octopuses are active predators, intelligent, mobile, flexible in their dietary habits. The presence of octopuses in ice shelf cavities implies that there is a food web complex enough to support a top predator. Whatever they are eating, fish, invertebrates, smaller cephalopods, implies the presence of a community more diverse and more energetically rich than the simple presence of sponges would suggest. The octopus, in this sense, is an ecological indicator. Its presence tells us something important about the richness of the community in which it lives. The octopus brings us, naturally enough, to the broader subject of cephalopod biology in Antarctic waters, which is one of the most fascinating chapters in marine biology. The Southern Ocean is home to an extraordinary diversity of squid and other cephalopods, including some of the most remarkable and least understood animals on the planet. The colossal squid, Mesonychotuthis hamiltoni, is the largest of all cephalopods and by mass, the largest invertebrate on Earth. We mentioned it briefly in the first part of our exploration, but it deserves more attention. The colossal squid lives in the deep waters of the Southern Ocean, typically at depths of 2,000 meters or more, and it hunts by ambush, a sluggish, slow-moving predator that waits for prey to come to it rather than actively chasing it down. This is an energy-efficient strategy, well-suited to the cold, food-sparse environment of the deep Southern Ocean. The colossal squid's eyes are the largest of any animal on Earth. They can reach a diameter of 27 centimeters, roughly the size of a soccer ball. These enormous eyes are adapted to the dim twilight of the deep ocean and are particularly sensitive to the bioluminescent flashes produced by many deep-sea organisms. Some researchers believe the colossal squid may use its remarkable eyes to detect the bioluminescence of sperm whales, which also hunt in the deep Southern Ocean, allowing it to avoid these predators despite its own sluggish pace. The sperm whale, which preys on colossal squid, often carries sucker scars on its skin that indicate the squid puts up a significant fight when attacked. The colossal squid is so rarely observed alive that almost everything we know about its behavior comes from examination of dead or dying specimens, animals that have been caught in fishing nets or found in the stomachs of sperm whales. The first complete adult specimen was not captured until 2007, and since then only a handful of complete specimens have been obtained. We do not know how long colossal squid live, how they reproduce, what their social behavior, if any, looks like, or how large the largest individuals actually grow. Estimates of maximum size range from approximately 12 feet to, in some speculative estimates, considerably larger, though the lack of confirmed giant specimens makes the upper end of those estimates uncertain. What we do know is that the colossal squid plays an important role in the Southern Ocean food web, both as a predator and as prey. The quantity of colossal squid consumed by sperm whales alone, estimated from the frequency of colossal squid remains in whale stomachs and the population size of sperm whales in the Southern Ocean, is very large, and the colossal squid must itself be consuming large quantities of fish and other organisms to sustain itself. This animal, which was essentially unknown to science until the 20th century, is now recognized as a significant functional component of one of the world's most important ocean ecosystems. Now let us turn our attention skyward, away from the ocean and the ice and the bedrock, and toward the sky above Antarctica, because the atmosphere and the cosmos above the southern polar region have been the subject of some of the most important scientific observations in the history of astronomy and atmospheric science. Antarctica is one of the finest astronomical observation sites on Earth, for reasons that are both meteorological and geographical. The polar plateau, the high, flat expanse of East Antarctica, centered on the South Pole, is one of the driest places on Earth in terms of atmospheric water vapor. Water vapor is a major source of interference for many kinds of astronomical observation, particularly at infrared and submillimeter wavelengths that are crucial for studying cool objects in the universe, galaxies in the process of forming, the cold dust and gas clouds where stars are born, the cosmic microwave background radiation. At the South Pole, the extremely low humidity means that the atmosphere is nearly transparent at these wavelengths during much of the year. Additionally, the polar location means that the sky does not rotate overhead as it does at lower latitudes. A telescope at the South Pole pointed at a celestial object near the South Celestial Pole will track that object continuously, day after day, without it rising and setting as it would from any other location on Earth. This allows for observations of extraordinary duration, years-long monitoring of particular objects or regions of the sky that would be impossible from any other location. The South Pole Telescope, a large submillimeter wavelength instrument located at the Amundsen Scott South Pole Station, has made important contributions to our understanding of the cosmic microwave background, the faint, all-pervasive glow of microwave radiation that is the afterglow of the Big Bang, imprinted on the universe when it was approximately 380,000 years old. By mapping the tiny temperature variations in this radiation, variations that amount to only millionths of a degree, the South Pole Telescope and similar instruments have provided crucial tests of cosmological models and have helped to establish our current understanding of the composition and evolution of the universe. The measurements made by Antarctic telescopes have confirmed that the universe is approximately 13.8 billion years old. They have established that ordinary matter, the atoms of which stars, planets, and people are made, accounts for only about 5% of the universe's total energy content. The rest is divided between dark matter, about 27%, and dark energy, about 68%, two of the most profound mysteries in all of physics. These are not small or peripheral scientific results. They are among the foundational discoveries of 21st century science, and they were made, in significant part, from telescopes and detectors operating in the extreme cold and isolation of the Antarctic ice sheet. Also located at the South Pole is one of the most unusual scientific instruments ever built, the IceCube Neutrino Observatory. IceCube is not a telescope in the conventional sense. It does not collect light. Instead, it detects neutrinos, fundamental particles that have almost no mass and interact with matter so weakly that they can pass through the entire Earth essentially unimpeded. Neutrinos are produced in enormous quantities by high-energy processes in the universe. Supernovae, the accretion disks around black holes, the cores of active galaxies, and studying them can provide information about these extreme environments that is inaccessible through any other means. IceCube works by detecting the rare occasions when a high-energy neutrino does interact with matter, specifically with the ice of the Antarctic ice sheet. When a neutrino collides with an ice molecule, it can produce a secondary particle that travels through the ice faster than light can travel through ice. Light travels slower in a medium like ice than in vacuum, and matter particles can exceed this reduced speed without violating any physical laws. When a charged particle travels faster than light in a medium, it produces a flash of blue light, a phenomenon called Cherenkov radiation. IceCube detects these Cherenkov flashes using an array of thousands of optical sensors embedded in the ice at depths from 1,450 to 2,450 meters, covering a cubic kilometer of Antarctic ice. The ice at these depths is extraordinarily clear, some of the most optically transparent ice anywhere on Earth, formed from snow that fell hundreds of thousands of years ago and was compressed under immense pressure to a state of remarkable purity. This clarity is essential for IceCube's function. The Cherenkov light from a neutrino interaction must travel through hundreds of meters of ice to reach the nearest sensors, and any impurity or optical distortion would scatter the light and destroy the information about the direction and energy of the original neutrino. IceCube has made a series of remarkable discoveries. In 2013, it reported the first detection of high-energy cosmic neutrinos coming from outside our galaxy, produced by processes of extraordinary violence in distant parts of the universe. In 2018, it linked a high-energy neutrino event to a specific source. A blazar, a galaxy with an actively feeding supermassive black hole pointed almost directly at Earth, called TXS 506+056. This was the first time a specific astrophysical source had been identified for a cosmic neutrino, and it opened a new chapter in the field of multi-messenger astronomy, the combined study of cosmic events using light, gravitational waves, and now neutrinos simultaneously. These are not obscure or specialized results. The detection of cosmic neutrinos and the identification of their sources addresses some of the most fundamental questions in high-energy astrophysics. Where do the most energetic particles in the universe come from? What are the physical processes at work in the most extreme environments the universe produces? And how do we extract information about the cosmos from particles that interact with matter so weakly that the entire Earth is essentially transparent to them? All of these questions are being addressed in part with an instrument buried in the ice of Antarctica, an instrument that exists where it exists because the ice of Antarctica is uniquely suitable for its purpose. Let us return now to the ice itself, not to the ice sheets and glaciers as subjects of climatological concern, but to the ice as a physical and chemical wonder in its own right. Because water ice, which we tend to think of as one of the most familiar and mundane substances in the world, turns out to be one of the most complex and scientifically interesting materials on Earth. Most people know that water is unusual among common substances in that its solid form, ice, is less dense than its liquid form. This is why ice floats. It is a consequence of the particular geometry of water molecules and the hydrogen bonds that form between them when water freezes, and it has consequences that are enormously important for life. If ice sank rather than floated, lakes and ponds and eventually the oceans themselves would freeze from the bottom up, and the life that depends on liquid water would have a much harder time persisting through cold periods. But ice is far more complex than this single unusual property suggests. There are, at last count, at least 19 distinct crystalline forms of water ice, each stable under different conditions of temperature and pressure. The ice we encounter in everyday life, ice cubes, frost on windows, the ice on a winter road, is ice, the hexagonal crystalline form stable at normal pressures and temperatures below 0 Celsius. But at the extreme pressures found deep within ice sheets, or at the pressures found in experimental laboratories, water freezes into different crystalline structures with different properties. The ice deep within the Antarctic ice sheet is not simply compressed hexagonal ice. As ice layers accumulate over thousands of years and are buried progressively deeper, the pressure increases and the ice crystals reorganize and grow, reaching sizes that can be visible to the naked eye. The orientation of these crystals, which way their crystalline axes are pointing, affects how the ice flows, which in turn affects the dynamics of the ice sheet and how it moves toward the ocean. Understanding ice crystal orientation at different depths in the ice sheet is therefore not merely an academic exercise in crystallography. It is directly relevant to modeling the flow of the ice sheet and projecting its future behavior. Researchers drilling ice cores for climate records must navigate these physical properties carefully. As the drill descends into the ice, the changing temperature and pressure conditions affect the ice in ways that can cause the core to fracture or the borehole to close. Drilling fluids are used to keep the borehole open, but the choice of drilling fluid and the drilling technique must be adapted to the changing conditions. The deepest ice cores, the ones that contain the oldest ice and the most ancient air bubbles, are the most difficult to extract and the most fragile to handle, requiring extraordinary care and skill. The air bubbles themselves, the ancient atmospheric samples preserved within the ice, are worthy of a moment of reflection because they are something genuinely remarkable. Think about what they are. They are samples of the actual atmosphere of Earth from hundreds of thousands of years ago, the actual air that was breathed by Homo erectus, by Neanderthals, by every creature that lived during the long oscillation of ice ages and interglacials. When you analyze an air bubble extracted from a 400,000-year-old ice core, you are measuring the actual composition of the actual air that surrounded the actual living world of that ancient time. You are not inferring it from proxy measurements or modeling it from geological records. You are measuring it directly. That is extraordinary. It is a form of time travel, not of people, but of data. The ice has preserved information about the past in a form that can be directly read in the present, and that information is telling us things we could not know in any other way. The oldest ice cores currently available extend back approximately 800,000 years. But the search for older ice, for the oldest ice project we mentioned earlier, is driven by the recognition that the period just beyond the reach of current cores, the period from about 800,000 to 1.5 million years ago, is one of the most scientifically important intervals in quaternary climate history. This is the period during which the rhythm of ice ages changed, shifted from 41,000-year cycles driven by one particular wobble in Earth's orbital parameters to 100,000-year cycles whose driving mechanism is still debated. Ice cores from this period would contain direct records of atmospheric greenhouse gas concentrations through this transition, potentially allowing scientists to determine once and for all whether the shift in ice age rhythm was driven by changes in greenhouse gas concentrations, changes in ice sheet dynamics, or some combination of both. Finding the right location for the oldest ice drill site has been a major scientific challenge. The ice must be thick enough to have accumulated over the relevant time period, more than 1.5 million years of snowfall. But if the ice is too thick, the oldest layers at the bottom will have been compressed into an extremely thin band, and the time resolution of the record will be too poor to be useful. The ice must also be cold enough and dry enough that the oldest layers have not been disturbed by melting at the base of the ice sheet. And the accumulation rate of snow must be low enough that individual annual layers are compressed to a manageable thinness at depth without being entirely destroyed. Finding a location that meets all of these criteria simultaneously requires extensive ground-penetrating radar surveys, ice flow modeling, and a good deal of scientific judgment and some luck. The current best candidate sites are in specific areas of East Antarctica where the ice thickness, accumulation rate, and basal temperature conditions appear to be most favorable. Preliminary drilling has already begun at some of these sites, and the scientific community is watching with intense interest, knowing that the first cores to come up from the critical depth interval will contain information that will reshape our understanding of quaternary climate dynamics. We should spend time now with one of the most dramatic and visually striking phenomena associated with Antarctica, one that combines physics, chemistry, and biology in a display of extraordinary beauty: the phenomenon of bioluminescence in Antarctic waters. Bioluminescence, the production of light by living organisms through chemical reactions, is one of the wonders of the marine world. It is far more common in the ocean than most people realize. The majority of marine animals capable of independent movement are estimated to be capable of producing light. In the open ocean at night, and particularly in the deep ocean, bioluminescence is the dominant light source, a universe of living light, flashing and glowing and pulsing in the darkness, for purposes of communication, predator avoidance, prey attraction, and species recognition. In Antarctic waters, bioluminescence takes on particular significance because of the seasonal extremes of light and dark. During the Antarctic winter, the surface waters experience months of complete darkness. The sun never rises above the horizon, and the only light in the ocean comes from the organisms themselves. In these conditions, bioluminescence is not just a supplementary communication system. It is the primary visual medium through which organisms perceive and interact with one another. The winter Antarctic Ocean, in this sense, is a world that operates almost entirely on biological light. Krill, the foundational animals of the Southern Ocean food web, are themselves bioluminescent. They produce blue-green light from photophores, specialized light-producing organs, located on their undersides. The function of this bioluminescence is not entirely clear, but the leading hypothesis is that it is counterillumination. By producing light on their undersides that matches the dim, downwelling light from the surface, krill can make themselves less visible to predators looking up from below, effectively hiding their silhouette against the background light. This is an elegant adaptation that has evolved independently in multiple groups of marine organisms. Many of the deep-sea squid of the Southern Ocean are also bioluminescent, using light for a variety of purposes: to communicate with potential mates, to confuse predators with sudden bright flashes, to attract prey by mimicking the bioluminescent signals of organisms that their target animals are interested in. Some species have photophores of extraordinary complexity, tiny, compound structures with lenses and reflectors and color filters that allow the production of precisely controlled light signals. The sophistication of these biological optical systems rivals anything in our own technology. The study of bioluminescence in Antarctic waters is still in its relative infancy. The difficulty of conducting nighttime observations in such a remote and extreme environment has limited what we know. But advances in sensor technology, in autonomous vehicles capable of sustained nighttime operation, and in optical detection methods sensitive enough to record the faint, transient flashes of biological light in the open ocean, are beginning to open this world to systematic investigation. What we are finding is that the bioluminescent life of the Southern Ocean is both more diverse and more ecologically important than was previously suspected. Now let us return to the surface, to the world of ice and rock and cold that most people think of when they think of Antarctica, and spend some time with the most visible, most photographed, most iconic inhabitants of the continent, its seabirds and penguins. Antarctica and the islands of the Southern Ocean are home to an extraordinary diversity and abundance of seabirds. Albatrosses, petrels, skuas, terns, and of course penguins, these animals have adapted to one of the most demanding environments on Earth, and their adaptations are both physically remarkable and behaviorally sophisticated. The wandering albatross, Diomdia exulans, is in many ways the supreme achievement of seabird evolution. With a wingspan reaching 12 feet, the largest of any living bird, it is built for a life in the air over the Southern Ocean, and that life is almost incomprehensibly vast in its scope. Wandering albatrosses spend most of their lives at sea, covering enormous distances on wings held rigid, gliding on the powerful winds of the Southern Ocean with minimal expenditure of energy. Satellite tracking of individual birds has revealed that they can travel 75,000 miles or more in a single year, circumnavigating the globe multiple times in the course of their foraging travels. They can live for 50 years or more, among the longest-lived of all birds, and they return to land only to breed at specific island colonies where the same individuals return year after year to the same nesting sites. Albatrosses are also among the most socially and emotionally complex of birds. They have elaborate courtship dances, multi-step, highly formalized sequences of movements and calls that are unique to each pair, and that pairs maintain and refine over years of partnership. Pairs bond for life, or very nearly so, separating only in the rare cases where repeated breeding failures prompt one partner to seek another mate. The investment that albatrosses make in each breeding attempt is enormous. They raise only a single chick per breeding season, and breeding seasons are so long from egg-laying to fledging takes nearly a year that successful pairs breed only in alternate years. Penguins, of course, are the most iconic Antarctic animals, and they are extraordinary in their own right. There are 18 species of penguin in the world, though only a subset of these actually breed on the Antarctic continent or its immediate offshore islands. The emperor penguin, Aptenodytes forsteri, is the largest of all penguins, and its breeding biology is among the most remarkable of any animal on Earth. Emperor penguins breed in the Antarctic winter, during the coldest, darkest months of the year, in conditions of murderous cold, because their chick-rearing schedule is timed so that the chicks will be large enough to fend for themselves by the time the summer sea ice breaks up and the open ocean becomes accessible. The breeding cycle begins in March or April, when emperor penguins trek inland from the sea ice edge to their breeding colonies. The female lays a single egg in May or June and immediately transfers it to the male, who balances it on his feet, covering it with a fold of warm abdominal skin called a brood pouch. The female then returns to the sea to feed, leaving the male to incubate the egg through the full depth of the Antarctic winter. The male emperor penguin's incubation vigil is one of the most extraordinary behavioral feats in the animal kingdom. For approximately 65 days in temperatures that can drop to minus 60 degrees Celsius and with wind speeds that can exceed 120 miles per hour, the male stands on the ice, incubating his egg, eating nothing. He survives this ordeal through a combination of physiological adaptation. His metabolism slows dramatically, his heart rate drops, he conserves heat with extraordinary efficiency and behavioral thermoregulation. The males huddle together in tight groups, rotating constantly through the huddle, so that each individual spends time both in the wind-exposed outer layers and in the warmer interior of the group. The huddling behavior is not simply a matter of physical contact. It is a coordinated, dynamically organized system in which the movements of thousands of individual birds create a slowly rotating group structure that distributes warmth more or less equitably among all members. When the female returns, timing her return to approximately coincide with the hatching of the egg, the male has lost up to half his body weight. If the female is late, the male will feed the newly hatched chick a special secretion produced by the esophagus, an emergency food supply that can sustain the chick for a few days until its mother's arrival. If the female does not return in time, the chick dies, and both parents' enormous investment in the breeding attempt is lost. This biology, this extraordinary commitment of energy and time and risk to a single offspring, reflects something fundamental about the selective pressures operating on emperor penguins in their extreme environment. Resources are scarce. The timing of the season is critical. There is no room for multiple breeding attempts or for spreading investment across multiple offspring. Everything rides on one egg, one chick, one season. And the penguin's behavioral and physiological adaptations are precisely calibrated to maximize the chances of success under these demanding conditions. The study of penguin colonies has also provided important insights into the effects of environmental change on Antarctic wildlife. Penguin populations are sensitive indicators of changes in sea ice extent, ocean temperature, and prey availability, and long-term monitoring of penguin colonies, some of which has been ongoing for decades, has documented population changes that reflect broader ecological changes in the Southern Ocean. Some penguin species are declining. Adelie penguins, medium-sized penguins that depend heavily on sea ice, are declining in some parts of their range where sea ice is becoming less extensive or less predictable. Emperor penguin populations are a source of particular concern because the timing of sea ice formation and breakup is crucial to their breeding success, and models project significant changes in sea ice conditions over the coming decades. Some scenarios project dramatic declines in emperor penguin populations by the end of the century, as the sea ice conditions on which their breeding biology depends deteriorate. But other penguin species are actually increasing in some areas. Chinstrap penguins and gentoo penguins, which are less dependent on sea ice and more flexible in their dietary habits, have expanded their ranges and increased their populations in some areas, taking advantage of the ecological changes that are disadvantaging other species. The picture is complicated and varies significantly by species and location, but the overall trend of an ecosystem responding to significant change, with some species losing and others gaining, is clear. Let us now return to the question of ice sheet stability and take a more comprehensive look at what is happening across the continent, not just at Thwaites but across the full extent of the Antarctic ice sheets. Because Thwaites, as important as it is only one part of a larger story. The Antarctic ice sheet is losing mass. This is not a matter of scientific controversy. It is one of the most clearly established facts in contemporary Earth science, measured by multiple independent methods using satellite altimetry, measuring the height of the ice surface from space, satellite gravimetry, measuring changes in the gravitational field caused by changes in ice mass, and direct field measurements. The most recent comprehensive assessments indicate that Antarctica is losing ice at an accelerating rate. The rate of loss is greater now than it was a decade ago, which was greater than it was a decade before that. The details, however, are complex and regionally variable. The vast majority of the ice loss is coming from West Antarctica, and specifically from the glaciers draining the Amundsen Sea sector, Thwaites, Pine Island Glacier, Smith Glacier, and their neighbors. These glaciers are all responding to the same driver, the intrusion of warm circumpolar deep water beneath their ice shelves, driven by changes in wind patterns that are themselves connected to broader changes in the climate system. East Antarctica, which contains far more ice than West Antarctica, has been more stable. For most of the period of satellite monitoring, East Antarctica has been close to mass balance, the ice gained through snowfall roughly equaling the ice lost through glacial flow and melting. But recent years have seen evidence of acceleration in some East Antarctic glaciers as well, particularly in areas like Totten Glacier, a massive, potentially vulnerable glacier that drains a basin containing ice equivalent to several meters of sea level rise. Totten, like Thwaites, sits on bedrock that slopes downward toward the interior, making it potentially susceptible to the same kind of marine ice sheet instability that threatens West Antarctica. The Antarctic Peninsula, the long arm of land reaching toward South America, is a third region with its own distinctive ice loss story. The peninsula has experienced some of the fastest warming of any region on Earth over the past several decades, with temperatures rising several times faster than the global average. This warming has caused the collapse of several ice shelves on the eastern side of the peninsula, Most dramatically, the Larsen B ice shelf, which had existed for at least 10,000 years and collapsed in the space of approximately 6 weeks in 2002. When ice shelves collapse, the glaciers behind them that were flowing into the shelves accelerate dramatically. The shelf was acting as a buttress, slowing the flow of ice toward the ocean, and when it disappeared, the glaciers surged. Some of the glaciers draining into the former Larsen B area are now flowing several times faster than they were before the shelf collapse. The story of Larsen B is instructive both as a case study in ice dynamics and as a cautionary tale about the pace of change. Before 2002, the conventional wisdom was that large ice shelves like Larsen B were stable features that changed over centuries or millennia, not over years or decades. The rapid collapse of Larsen B demonstrated that this assumption was wrong, that ice shelves can reach tipping points and collapse catastrophically, in geological terms almost instantaneously. This realization has fundamentally changed how glaciologists think about ice shelf stability and has informed concerns about other ice shelves, including the Thwaites ice shelf, whose stability is now closely monitored for signs of the kind of fracturing and rifting that preceded the Larsen B collapse. The story of ice loss in Antarctica connects, of course, to the broader story of sea level rise, a story that is playing out slowly enough that it can seem abstract, but that has already caused measurable effects and that will cause increasingly significant effects over the coming decades and centuries. Sea levels globally have risen by approximately 20 centimeters, about 8 inches, over the course of the 20th century, and the rate of rise has accelerated in recent decades. Antarctica currently contributes roughly a quarter of observed sea level rise, with the rest coming from the melting of other glaciers and ice sheets around the world and from the thermal expansion of ocean water as it warms. The projections for future sea level rise from Antarctica range widely, reflecting genuine scientific uncertainty about the dynamics of marine ice sheets and the possibility of rapid, non-linear changes. Conservative projections suggest a few tens of centimeters of sea level rise from Antarctica by 2100. More alarming projections, based on scenarios involving the activation of marine ice sheet instability and the collapse of ice shelves, suggest that contributions of a meter or more from Antarctica alone are possible before the end of the century, and that over the next several centuries, several meters of sea level rise from Antarctica cannot be ruled out. What does a meter of sea level rise mean? It means that storm surges, the temporary increases in sea level caused by hurricanes and other severe weather events, become significantly more destructive, reaching areas that were previously above their reach. It means that low-lying coastal areas, particularly in river deltas, are permanently inundated or become more vulnerable to flooding. It means that saltwater intrudes into freshwater aquifers that coastal communities depend on for drinking water. It means that the infrastructure of coastal cities, ports, airports, roads, buildings must be either protected at enormous cost or eventually abandoned. These are not distant or hypothetical consequences. They are already being felt in low-lying areas around the world, and they will intensify as sea level rise continues. The ice of Antarctica is not just a scientific curiosity. It is a bank of potential sea level rise that will shape the geography of human civilization over the coming centuries. Understanding it, its dynamics, its vulnerabilities, its likely behavior under different climate scenarios is one of the most important scientific challenges of our time. Let us now turn, as we approach the final chapters of our journey through this extraordinary continent, to the question of the future of Antarctic research, to what is coming, what tools and technologies and approaches scientists are developing to push the boundaries of what we know about this continent and what we can learn from it. The development of autonomous systems, underwater vehicles, aerial drones, surface robots, is transforming Antarctic science in ways that are still unfolding. We have discussed the autonomous submarine RAN and its mission beneath Thwaites. But RAN is one of a rapidly growing family of autonomous vehicles specifically designed or adapted for Antarctic conditions, and the science they are enabling is extraordinary in its scope and ambition. Underwater gliders, autonomous vehicles that change their buoyancy to move through the ocean, covering enormous distances on very little power, have been deployed in the Southern Ocean for years-long missions, collecting continuous profiles of temperature, salinity, oxygen, and other properties at depths up to 1 kilometer or more. These vehicles can survive in conditions that would prevent ship-based observations for months at a time. The winter Southern Ocean, with its ice and its violent storms, is essentially inaccessible to research ships for a large part of the year. Gliders do not care about storms. They continue their patient, slow journeys through the water, collecting data during conditions that no human crew would venture into. Aerial drones, both fixed-wing and multirotor, are being used increasingly for surveys of ice surfaces, wildlife colonies, and coastal geology. A drone can cover in a day terrain that would take a team of scientists on foot weeks to survey. It can access places that are dangerous or physically impossible for people to reach, the faces of calving glaciers, the summits of nunataks, the interiors of deep valley systems. And it can collect photographic and sensor data of a quality and consistency that is difficult to achieve with traditional methods. Ice-penetrating radar, instruments that send radar pulses into the ice and detect the echoes from internal layers and from the bedrock below, has been a staple of Antarctic geophysics for decades, flown on aircraft and towed behind snowmobiles to map the sub-ice topography. But the technology continues to improve, and new generations of ice-penetrating radar are revealing details of subglacial geology, sub-ice topography, and internal ice structure that were previously invisible. The mapping of sub-ice topography across Antarctica is still incomplete. There are significant areas of the continent where the bedrock beneath the ice has never been mapped in detail, and the continued development and deployment of ice-penetrating radar is a high priority for Antarctic glaciology. Satellite observation has been and will continue to be central to Antarctic science. The continuous global coverage that satellites provide, measuring ice surface elevation, ice velocity, ice shelf extent, sea ice concentration, ocean surface temperature, atmospheric composition, and many other parameters, is irreplaceable. New satellites with improved sensors, better temporal resolution, and longer operational lifetimes are regularly being added to the constellation of instruments monitoring Antarctica from orbit. And the development of new analytical techniques, machine learning, artificial intelligence, data fusion from multiple sensor types, is enabling scientists to extract more and more information from the mountains of satellite data that are now available. The future of Antarctic science is also being shaped by advances in biological sampling and analysis. Environmental DNA, the genetic material shed by organisms into their environment, whether into water, soil, or air, can be collected from environmental samples and analyzed to reveal what organisms are present in a given place, even if those organisms are never directly observed. This technique, eDNA metabarcoding, is being applied to Antarctic environments with growing enthusiasm, because it offers a way to survey biological communities in places and conditions where traditional survey methods are impractical. Imagine being able to filter a liter of water from beneath an ice shelf and determine, from the genetic material in that water, not just whether any animals are present, but what species are there, which fish, which invertebrates, which microbes. Imagine being able to do this without ever needing to see any of those organisms, without any physical evidence beyond a water sample. This is what eDNA metabarcoding offers, and its application to Antarctic environments is already yielding remarkable results. Communities previously thought to be simple and sparse are turning out to be considerably more diverse than anyone suspected, because the genetic traces of organisms that are rarely observed are present in the water even when the organisms themselves are absent from direct observation. The application of genomics, the comprehensive study of an organism's genetic material, to Antarctic organisms is also opening new windows into the biology of adaptation to extreme conditions. By comparing the genomes of Antarctic organisms with those of their non-Antarctic relatives, scientists can identify the specific genetic changes that underlie adaptation to cold, darkness, and other extreme conditions. These comparisons can identify genes that have been amplified or modified to support the production of antifreeze proteins, the maintenance of membrane fluidity at low temperatures, the efficient use of scarce nutrients, and many other adaptations. And because these genetic adaptations represent solutions to physical and chemical problems that are universal, cold temperatures, limited energy, high pressure, they can potentially inform the development of biotechnological applications that have nothing to do with Antarctica. As we approach the end of our exploration, I want to step back once more and consider something that has been implicit throughout our entire journey but deserves to be stated explicitly. This is the question of what Antarctica means not as a scientific subject, but as a concept, a symbol, a presence in the human imagination. Antarctica is the last great wilderness. It is the one place on Earth that has never been permanently settled by human beings, that has no indigenous population, no permanent residents in the full sense, no traditions of ownership or belonging stretching back into the deep past. It belongs, in the formal legal sense established by the Antarctic Treaty, to no nation but to humanity as a whole, a commons of the most unusual kind, a place held in trust for science and peace by international agreement. This status as a wilderness, as a commons, as a place of science rather than exploitation is both remarkable and fragile. The Antarctic Treaty has been remarkably successful over its more than 6 decades of operation. The continent has remained demilitarized. Scientific research has continued uninterrupted through periods of political tension between signatory nations. The environmental protections established by the Protocol on Environmental Protection to the Antarctic Treaty, the Madrid Protocol, adopted in 1991, have prevented the exploitation of mineral resources and established Antarctica as a natural reserve devoted to peace and science. But the treaty faces pressures. The discovery of significant mineral and hydrocarbon resources, coal deposits in the Transantarctic mountains, potential offshore oil and gas reserves, has made Antarctica potentially attractive to resource extraction interests, even though the Madrid Protocol currently prohibits such extraction indefinitely. The growing strategic importance of the Southern Ocean as shipping lanes change with sea ice conditions, and as access to resources in the broader region becomes economically significant, means that national interests and geopolitical calculations are never far from the surface of Antarctic affairs. And the increasing number of nations with significant Antarctic presence and programs, including nations that were not among the original treaty signatories and that may not share all of the values that drove the treaty's creation, adds complexity to the governance of this unique commons. The scientific community has been and must continue to be a powerful voice for the preservation of Antarctica's status as a place of science and environmental protection. The scientific case for why Antarctica must remain as it is, a natural laboratory, a climate archive, an ecological reference system, a place where the Earth systems can be studied in conditions relatively unaffected by direct human alteration, is powerful and well established. But it must be made and made repeatedly because the pressures that threaten to compromise Antarctica's protected status are real and not going away. There's one final story from Antarctica that I want to tell before we conclude our journey, because it brings together almost everything we have discussed: the extreme biology, the geological history, the climate science, the astrobiology, and the human dimension in a single remarkable package. It is the story of the discovery of microbial life in the deep subsurface of the Antarctic ice sheet itself. Not under the ice sheet in subglacial lakes, we have already talked about that. Not in sub-ice shelf cavities, we have talked about that too, but in the ice itself, inside the ice, living in the water films that form between ice crystals, in the liquid inclusions within the ice, in the thin veins of brine that permeate the ice sheet even at temperatures well below the bulk freezing point of water. Ice, it turns out, is not as solid as it appears. At the boundaries between individual ice crystals, there is always a thin film of disordered water, a quasi-liquid layer that remains unfrozen because of the surface energy effects at the crystal grain boundaries. The thickness of this layer depends on temperature and on the chemistry of the water, but even at temperatures of -20 Celsius, the grain boundary water films are thick enough to potentially sustain microbial life. And in the presence of solutes, salts, organic compounds, the freezing point is depressed further, allowing thicker liquid layers to persist at even lower temperatures. The microorganisms found living in these ice grain boundary films are among the most cold-adapted organisms ever discovered. They are metabolically active, they are doing chemistry, consuming energy, maintaining themselves at temperatures that would kill virtually every other known organism outright. They have developed enzymes that function at these temperatures, molecular machines built from proteins that fold into their functional shapes and carry out their catalytic roles in conditions that would cause the proteins of most organisms to become rigid and non-functional. How do they obtain energy? How do they sustain themselves in an environment where resources are almost unimaginably scarce? The answers are still being worked out, but they appear to involve the scavenging of trace organic compounds from the ice itself, organic material that was incorporated into the ice when it formed from ancient snow, that has been preserved within the ice for thousands of years, and that is slowly being accessed by these extraordinary microorganisms. In a sense, these ice-dwelling microbes are feeding on the past, consuming the organic legacy of ancient surface ecosystems preserved within the ice. The existence of microbial life within the Antarctic ice sheet has profound implications. It means that the ice itself, which covers nearly 14 million square kilometers of Antarctica, is not lifeless. It is inhabited, however sparsely, however marginally, however at the very edge of what is physically possible. It is another addition to the growing list of environments, each one more extreme than the last, in which life has found a way. And it means something for our understanding of cold, icy worlds elsewhere in the solar system. The ice shells of Europa, Enceladus, and other icy moons are not just barriers to the liquid water oceans that may lie beneath them. They might be habitats in their own right, home to organisms as tenacious and resourceful as those that inhabit the ice of Antarctica. The possibility space for life in the universe, already expanded enormously by the discoveries of Antarctic subglacial lakes, sub-ice shelf communities, and chemosynthetic ecosystems, expands further still. We have traveled a long way together on this journey. We have gone from the conspiracy theories and the legends to the cutting edge of Earth science and astrobiology. We have visited the blood falls and heard the songs of blue whales. We have gone beneath the ice with autonomous submarines and read the ancient atmosphere in the bubbles of ice cores. We have met the bacteria that breathe sulfate and the octopuses that carry antifreeze in their blood. We have stood at the edge of the Thwaites Glacier and contemplated what its future holds for the rest of us. We have looked at the cosmos through telescopes on the ice and detected neutrinos from distant blazars in the fabric of the ice itself. And through all of this, one thing has become absolutely clear. Antarctica is not a remote irrelevance. It is not a frozen wasteland at the bottom of the world, disconnected from the lives of the billions of people who will never visit it. It is one of the most important places on Earth, important for its science, important for its ecology, important for its role in the climate system, important for what it is telling us about the past and what it is showing us about the future. The ice is speaking. It speaks in the language of ancient air bubbles and accelerating glaciers, in the language of bioluminescent krill and endolithic microbes, in the language of cosmic neutrinos and primordial zircon crystals. It speaks of a planet that is ancient and dynamic, of a biosphere that is resilient and inventive, of a universe that may be far more full of life than we have dared to imagine. Learning to hear what the ice is saying, developing the science, the technology, the international cooperation, and the sustained commitment that this requires is one of the great tasks of our time. Antarctica has been keeping its secrets for a long time. We are only just beginning to learn how to ask the right questions. The continent waits at the bottom of the world, patient and enormous, as it has waited through the rise and fall of mountain ranges, through the coming and going of ice ages, through the entire span of human history and deep into the time before. It will wait as long as it takes. The question is whether we will be paying attention. Thank you for joining us on this extraordinary journey into the heart of the most mysterious continent on Earth. Antarctica has given us much to think about, much to wonder at, much to be humbled by, much to be inspired by. The science of this continent is one of the great ongoing stories of human inquiry, and it is far from finished. Every season, every expedition, every ice core and autonomous vehicle and satellite overpass adds new chapters to a story that grows richer and more remarkable with each passing year. If this journey has sparked your curiosity, if it has made you want to know more about the ice and the life it harbors and the climate it governs, then Antarctica has done what it does best. It has made the world seem larger, stranger, and more wonderful than you thought it was. And that, perhaps, is the greatest gift this frozen continent has to offer. Please let us know in the comments where you're watching from and what time it is for you. We love knowing that this community spans every corner of the globe, united by curiosity about this extraordinary world we share. Subscribe to the channel so you do not miss what is coming next. And until then, keep looking, keep asking, keep wondering. The ice is speaking. Are you listening?